It's working. Okay. Good morning. Wait, I want to set the virtual background.
Sorry, Dokter Tirsa, 7:55 clock kita already to live YouTube and webinar.
Oke.
Karena ada jeda 5 menit, jadi 5 menit sebelum jam 8 kita live duluan itu biar YouTube-nya serentak.
Oke, siap.
Nama aku kelihatan namaku kan ya?
Kelihatan dok, kelihatan.
Oke.
Dokter mau coba dengan virtual background.
Tak bisa karena di stop sama hostnya.
Videonya.
Heeh.
Ya, tadi saya juga gitu dok. Mungkin ada yang bisa buka all panelists the video. Pak Cepi.
Baik dok, bentar dok.
Oke, siapa?
Oke, please try check Dokter Sian.
Oke. Oke. Udah ya bisa ya? Oke.
Dokter Tirsa, saya mau share itu alurnya. Ada yang harus disampaikan terkait rules di awal dok.
Gimana Pak? Sorry Pak.
Sebentar, ada yang rule itu sudah saya buatkan slide-nya. Nanti akan kita tampilkan di awal dok.
Oke, ya. Pak Cepi mau coba dulu.
Ya, alurnya seperti ini nanti. Lalu oke ini dulu kita informasikan di awal.
Oke.
Ini yang tadi malam Dokter Tirsa buat.
Oke.
Kita mulai persiapan pembukaan.
Ya.
Saya tampilin CV Dokter Tirsa pada saat opening. Lalu nanti sesi Dokter Sian, CV, dan setelah sesi ini nanti saya turun screen, Dokter Sian masuk screen. Seperti itu dok.
Oke.
Ya, terima kasih.
Oke. Oke.
Ya, kita rehearsal sedikit ya Pak. Ini kan
Baik, Dok.
kelima ya. Oke, ini kan saya kan pertama kali kan nyambut. I greet everyone. So good morning everyone. I'm Tirsa and it's my pleasure to welcome each one of you present here at the collaboration of APFCB IACC webinar series, the ISO 15189-2022 Laboratory Accreditation Analytical Quality Requirement that is sponsored by SNIPE. I would like to greet Dr. Chan Xianhua, our first speaker. Good morning, Dr. Xian. I hope you are good today.
Good morning, Dr. Tisa.
And I also would like to greet Prof. Tony Patrick, our second speaker. Good morning, Prof. Patrick. How are you? And last but not least, I would like to greet Prof. Ken Sikaris, our third speaker. Good morning, Prof. Sikaris. And thank you very much for all the participants that already joined in the Zoom webinar on this Saturday morning. As we know, accreditation is an effective way to demonstrate competence of laboratory. A tool to recognize laboratories worldwide is linked to periodical audits, which leads to high standard of services to patients. In ISO 15189-2022 accreditation, the analytical processes requirements are in Clause 7.3 examination processes. The objective of these webinars are know and understand the scope of accreditation of ISO 15189-2022 and how to fulfill the technical and analytical requirement for laboratory accreditation. And this will be presented by first speaker. Second, understand concept of traceability, how to assure its traceability. Understand the role of IVD manufacturer in laboratory traceability will be presented by second speaker. And the third speaker will give the understanding how to count the uncertainty of measurement and also the benefit of using the uncertainty of measurement in the lab. And there are some rules for webinar. Ditampilin webinarnya dulu kali ya Pak?
Ini.
Rules. Ya.
Oh, berarti di setelah sisi Dokter Tirsa, saya kasih satu slide ini, Dok.
Ya.
Ya.
Jadi setelah saya greet everyone, saya kasih tahu webinar rules,
Ya.
terus sama pengumuman pelataran sehat.
Ya. Nah, sekarang dulu, Dok. Webinar rules opening saya CV Dokter Tirsa sebelum Dokter Sian penjelasan webinar lagi.
Oke.
Baik, Dok. Oh, banyak item-itemnya sebentar. Paling enggak.
Pagi-pagi udah ada yang nanya dong, LMS lantaran sehat.
Kang Cepi sudah ada video-video HKKI belum?
Belum, Pak.
Wih, harus cari dulu ntar ya.
Siap-siap.
Makasih Pak Kris. Pak Cepi. Jadi tadi
Baik, Dok.
urutannya kan welcoming participant, greetings, habis itu webinar rules, habis itu pengumuman pelataran sehat ya.
Oh ya, jadi webinar dulu baru pelataran sehat, Dok. Bentar saya balik.
Ya,
Webinar rule, pelataran sehat,
terus
terus welcome participant, opening ya.
opening tadi udah sih sekalian yang di awal aja Pak.
Oh, di awal aja ya.
Heeh,
Habis itu berarti habis webinar rule saya langsung CV
siap.
Dokter Tirsa ya.
Oh, oke. Ya,
CV
boleh.
Dokter Tirsa nanti pas menjelaskan itu apa? Saya pakai background judul judul webinar.
Oke. Pak Cepi, absen itu kita akan kasih linknya atau ditarik dari Zoom aja kan? Kita nggak kasih link kan?
Kalau ditarik dari Zoom dia nggak ada NIK-nya, Dok. Jadi eh ada dua backup sih sebenarnya. Yang pertama itu diminta di pos survei itu. Nah, terus yang kedua Pak Mizwar kan ada bikin automatic survei juga tuh yang via email. Nah, di situ ada juga
Ada link NIK-nya, ada itu NIK-nya ya.
ah, ada link NIK-nya. Tapi sebenarnya kalau narik dari data email yang hadir itu kan pada saat registrasi ada database ya yang ada NIK. Nah, STP itu tinggal nyocokin sih alamat email yang sama, nanti ketemu NIK dari situ bisa juga gitu.
Jadi nggak ada Google Form lagi keabsenan ya, Pak?
Iya Pak, gimana Pak?
Nggak ada Google Form absen ya, link
Nah,
atau
itu
gitu ya?
di link yang link yang Pak Mizwar kirim automatic email gitu Pak.
Artinya di chatbox kita nggak perlu tambahkan link Google Form lagi gitu.
Bebas kalau mau sih bisa dibuat. Apa mau dibikin aja ya?
Nggak usah. Justru
Nggak usah kalau gitu, biarin aja
Takutnya
mereka dengerin.
disebar. Kemarin tuh khawatirnya kalau dia baru ingat kemarin tuh kalau dikirim di chat nanti disebar linknya itu tuh jadi liar
Kemana-mana
Pak.
nanti.
Nah, malah jadi liar.
Bener, liar. Betul.
Tirsa, mungkin Dr. Tenny Bradrick sama Ken Sikaris mesti diingatkan kan ya kali ya.
Hmm?
Takut lupa dia.
Waduh, iya kok belum ada nih ya.
Iya.
Saya nggak punya WA-nya lewat mana ya?
Bentar, sebentar kalau Tony saya punya WA. Sebentar, saya WA.
Kemarin ada juga itu.
1 menit lagi saya buka peserta ya Dok, start webinar.
Oke, siap.
Suaranya pecah-pecah ya, di saya pecah.
Aman, Pak.
Oh, berarti di saya yang siap-siap.
Tapi videonya gerak. Musiknya doang. Ini udah oke. Sip.
Hitungan kelima kita live 3, 2, 1, 2, 3, 4 live.
Dikasih linknya bisa ya.
Ya Dok,
Untuk Dr. Tony dan Dr. Ken Sikaris.
mau ditunggu dulu.
Sudah di email ke beliau mestinya langsung itu.
Tadi dapat juga kan?
Dapat Dok, pasti Dok. Link
Oh,
panelis Dok.
Ada reminder juga kok.
Oh, oke.
Ada
Tadi pagi.
reminder tadi pagi Dok.
Oke, thank you.
Aku nggak dapet tuh Pak. Aku nggak dapet, makanya aku tadi minta itu.
Saya dapat jam 5.55. Ya. Bilang kasih ke si itu, siapa namanya yang suka didatengin itu.
Dok, kita live ya Dok. Peserta
Ini
saya
kita
mulai
harus mulai
masukkan
live
sekarang.
ini. Sebentar lagi, 2 menit lagi.
Dihubungin ini. Oke. Pengurukian bagian samaran. Tidak usah gitu.
Selamat pagi untuk peserta yang sudah masuk ke ruang Zoom. Kita akan mulai dalam 1 menit lagi. Okay, it's already 8 o'clock. Good morning, everyone. I'm Tirsa, and it's my pleasure to welcome each one of you present here at the collaboration of APFCB IACC webinar series, the ISO 15Jun2024 Laboratory Accreditation Analytical Quality Requirement that is supported by SNIPE. I would like to greet Dr. Xian Hua, our first speaker. Good morning, Dr. Xian.
Yeah. Good day, Dr. Tirsa.
I hope you are good today. And I would like also thank you very much for all the participants that already joined in the Zoom webinar on this Saturday morning. This morning, we have 3 speakers. One is Dr. Xian Hua. The second speaker is Prof. Tony Bedrick. And last but not least is Prof. Ken Sikaris. As we know, accreditation is an effective way to demonstrate competence of laboratory. A tool to recognize laboratories worldwide is linked to periodical audits, which leads to high standard of services to patients. In ISO 15189-2022 accreditation, the analytical processes requirements are in clause 7.3 examination processes. The objective of these webinars are, first, know and understand the scope of accreditation of ISO 15189-2022 and how to fulfill the technical and analytical requirement for laboratory accreditation. And this will be presented by first speaker. Second, understand the concept of traceability, how laboratory assure its traceability. Third, understand the role of IVD manufacturer in laboratory traceability, and these 2 goals will be presented by our second speaker. The fourth goal is understand how to count the uncertainty of measurement and understand the benefit of using the uncertainty of measurement in the lab, and this will be presented by our third speaker. Before we continue, I would like to read our webinar rules. Maybe can display the webinar rules. JP. For our webinar rules. Okay, first, the Q&A session will be held after the third presentation is finished. The participant can ask through Q&A. Please write down the questions and the question is asked to whom. Third, all participants can raise hands and ask directly to the presenter. So I will allow the participant to open the camera and ask directly to the presenter. Next, for participants in IACC YouTube channel, you can write down the questions in the comments column. Please do not forget to fill the presence, attendance, and post-webinar survey to get certificates. And for Indonesian participant, to get the continuing education credit points or SKP, please so the participants who will be given access to learning at the Healthy platform atau platform pelataran sehat are participants who follow Zoom until the end and are required to fill in the presence and post-webinar survey after the event ends. Let me, please allow me to speak in bahasa. Jadi untuk Bapak Ibu yang mengikuti seminar ini, untuk jika mau mendapatkan SKP atau akses di pelataran sehat, harus mengikuti Zoom sampai akhir dan mengisi kuesioner atau survei yang nanti akan di-emailkan, yang nanti akan diberikan. Untuk absen, itu tidak kita akan berikan berupa link, tetapi dari panitia akan memantau absen yang masuk di Zoom dan otomatis peserta yang masuk melalui Zoom itu akan mendapatkan email untuk absen serta link kuesioner. Dan bagi peserta untuk mendapatkan SKP Kemenkes harus menyelesaikan pretest dan posttest di pelataran sehat, pembelajaran di pelataran sehat. Dan akses untuk pelataran sehat akan dibuka pada hari ini setelah sesi Zoom pada pukul 5 sore sampai tanggal 22 Juni pukul 24.00. Jadi seluruh peserta mempunyai kesempatan untuk 1 minggu untuk boleh dapat mempelajari sesi hari ini. I will be as a moderator for this webinar session. So without overdue, let's welcome our first speaker, Dr. Chan Xianhua, the President of IACC and the head of APFCB Laboratory Management Committee. I would like to read Dr. Xian's CV. For Dr. Xian's CV. Okay, Dr. Xian is a medical doctor from Faculty of Medicine, University of Indonesia, Jakarta. And she took the Master of Science in Clinical Tropical Disease from Mahidol University, Bangkok, Thailand. And she's a clinical pathology from Faculty of Medicine, University of Indonesia, Jakarta. For Dr. Chan Xianhua, the time is yours.
Thank you, Dr. Trisa, for the kind introduction. Good morning, dear colleagues, ladies and gentlemen. My topic for today, let me share my presentation. My topic for today is the ISO 15189-2020. What's the difference and what laboratory should do? Well, as we all know that the ISO 15189-2012 has been superseded by the ISO 15189-2020. So by the year 2025, all laboratory following the ISO 15189 should all use the ISO 15189-2020. The ISO 15189-2022 specifies the requirement for quality and competence in medical laboratory, and it includes POCT. Medical laboratory in the ISO 15189 is the laboratory for examination of material derived from the human bodies for the purpose of diagnosis, monitoring, management, prevention, and also treatment of disease and assessment of health. And POCT, or point of care testing, according to the TS 22583-2019, is examination performed near or at the site of the patient. So, any laboratory that also perform tests outside of the laboratory itself, for example, when they perform tests at the ICU, high care, emergency, mobile unit, or home care, they should also apply the ISO 159-2022 requirement. For laboratory that use materials not derived from the human bodies, then the ISO 17025 apply. For example, the testing and calibration laboratories. What are the difference between the ISO 15189-2012 and the 2022 version? The major changes are the alignment of the document to the format of ISO 17025 and other ISO 17000 series. And it has greater emphasis on risk management and patient care. And in the ISO 15189-2022, there is the inclusion of requirement relating to the point of care testing because of the incorporation of the ISO 22870-2016 standard for POCT. And we can see also more details on some technical requirements. In the ISO 15189-2012, we are familiar with the requirement are divided into management requirement and technical requirement. But in this new version, the 2022, it is covered 5 requirements: the general requirements, structure and governance requirements, resource requirements, process requirements, and management system requirements. And as we all know, in the 2012 management requirements, there are many are covered in that requirement. But in the 2020, the organization and management responsibility, quality management system, advisory service was covered in the structural and governance requirement. And the service agreement, examination by referral laboratories, and external service and supplies are covered in the resources requirement. So laboratory has to get familiar with the new format. There is more emphasis in the requirement for the patient, such as we can see for the requirement in the 4.3 requirement for the patient. Laboratory management shall ensure the patient's well-being, safety, and rights are the primary consideration. Laboratories should implement confidentiality, impartiality, and also non-discrimination on every patient. And informed consent is acquired for every procedure. It can be verbal or written, according to relevance. And not only for the procedure, there is only informed consent for the giving information to other person, to third party or for public. And not only we have to respect the patient, but respect should also be given to the specimen and remnant. This is particularly applied in the histology services. And And laboratory has to make sure that all information are available for the patient, starting from the facility, service, method, turnaround time, cost, and also giving advisory services for the selection of tests, patient preparation, and also the interpretation of the result. Laboratory has to establish procedure and implement it, and for that procedure for identifying risk and also opportunity for improvement. And it includes the disclosure of incidents when it can cause harms to the patient. Examination offered to the patient should be periodically reviewed whether it is still appropriate for the clinical use. And the laboratory should also maintain the availability and integrity of all data, records, and sample in the event of merge, closure, or acquisition. That's currently common happen in the laboratory network. And also, emphasis are more in the risk management. Laboratory management shall establish, implement, and maintain processes for identifying risk, harm, and also opportunity for improved patient care. Not only identifying, it has to develop effective action to address both risks and opportunities. And in the implementation of the risk management, laboratory can use the ISO TS 22367 risk management in the medical laboratories, and also ISO 35001-2019 for the management of biorisks. Risk management should be applied in all aspects of laboratory operation. Laboratory that include risk identification and classification, risk assessment according to its severity and opportunity, its probability, and also laboratory has to prioritize which risk should be addressed. The risk that has been chosen should be analyzed for the root cause and strategy as implemented and continuously monitoring using the PDCA cycle. The sources for the risk identification can include, but not limited, by active finding, such doing prospective hazard and risk analysis process, review of is standard operation procedure, and it can also be found in the user reports, such user feedback, complaint, survey, near miss, or incidents report. Laboratory also can use the process monitoring reports, such as report of quality control and external quality assurance system. And also it can monitor its trend in the report. Other quality tools in the quality management system can be used, such as the quality indicator, audits report, and management review output. The ISO TS 22367 risk management for medical laboratory gives some tools for the assessment of the risk and also for the prioritizing the risk by the probability and severity. And there are also tools for the root cause analysis, such as the failure mode effect analysis, fishbone analysis, and the 7 whys. Option for the strategy to address the risk include avoiding the threat, eliminating risk, or it can also be reducing the risk or its consequences, transferring risk, taking a risk, but for an opportunity for improvement, or sometimes accepting risk for informed decision. It should apply to the needs of the laboratory after analysis the root cause and the opportunity. and the risks. All procedure and objective of the lab should all be documented and recorded. And so the do what you write and record what you do still apply in the ISO 15189-2022 requirement. Laboratory should document all the objective and the procedure, execute it or do it, and records what they have execute or do. All the documents should be communicated, reviewed, and updated, and all the records should be evaluated and stored to prevent it from unauthorized access or from damage. And retention time should be defined according to the regulation. In the 2022 version, the management system document can, but are not required to be contained in a quality manual. So the laboratory is not obliged to have a quality manual. The laboratory shall have available resources, that is personnel, facilities, equipment, reagent, consumable, and support services necessary to manage and perform its activity, including the resources for POCT. So we see the personnel, facility, and also support services that in 2012 requirement are not in the resources, now include in the resources. And in the support services include the agreement between laboratory users, with laboratory users or customer, POCT agreement, external suppliers, referral laboratories, ECAS provider, calibration for provider, consultant, and even the information system provider. All these resources should have laboratory should define qualification for all these resources. Establish selection procedure, verify that the qualification is met, and monitor whether the qualification is still attained. There is a clause in 6.8.2 regarding the referral laboratories and consultant. Here, the laboratory has the duty to communicate its requirement to the referral laboratories and consultant for the procedure, examination, report, and consulting activities to be provided, management of critical result, and any required personnel qualification and competence. It means laboratory has to see that all these requirements are in the agreement between the referral laboratory and consultant and the laboratory. Personnels mean internal or external personnels that could influence the laboratory activities. All personnel should have competency regarding education, specific qualification, induction and training, and also registration and working permit. And all these person in the 2022 version, there is a clause that regarding the management system awareness. It means that all these personnel should be aware of the relevant objectives and policy, their contribution to this management system, and the consequence of not conforming with this management system. So it, in other words, it means that they have to be aware and implement the ISO 15189-2022 standards. There is a clause regarding the authorization of specific tasks. The laboratory shall authorize personnel for selection, development, modification, validation, and verification of method, review, release, and reporting of result, and also authorize personnel for the use of laboratory information system, in particular, assessing, entering, and changing patient data or examination result. There is a there should be a record and a documented procedure for this. All the laboratory shall establish and maintain calibration and metrological traceability of its measurements result to the SI unit that include estimation of measurement of uncertainty and be made by accredited laboratories and validated method. It can be obtained by calibration by ISO 17025 accredited calibration lab, or by having certified reference material that provided that by competent producer that is accredited by ISO 17034, or with a certified reference material that is fulfilling the requirement of ISO 15194. There are no significant changes in the pre- and post-examination procedure, but there is a clause in the 7.2.7.3 considering the stability of the analyte. Laboratory has to specify and monitor the time between sample collection and the time when they perform the examination. It should be recorded, monitored, and reviewed. The laboratory shall select and use examination methods which have been validated for their intended use to assure the clinical accuracy of the examination for patient testing. So the laboratories should prefer method according the instruction of the use of the IVD instrument, or the method that is in the established textbook, or the peer review from peer review journal, or from the international or national recommendation, guideline, or regulation. Analytical requirements include validation or verification, uncertainty of measurement, reference interval or clinical decision limit, internal quality assurance, external quality assurance, and comparability of examination. I think this is not much different from the 2012 version. And all these analytical requirements should have specified criteria that should be obtained and should be periodically reviewed. In the 6.4.1, there is a clause that the equipment shall be used as specified by the manufacturer unless validated by the laboratory. So validation or confirmation that a specified intended use have been fulfilled should be done or performed for unvalidated validated method, laboratory design or developed method that is used outside their originally intended scope. For example, when lab use other manufacturer reagent or use specimen that not specified by the manufacturer, or when lab modified validated methods. And verification or confirmation of that specified requirement or intended use have been fulfilled should be performed with a validated method or IVD method. Verification and not validation can be performed if method is published in the established textbook or peer-reviewed text or journal, or method from international or national guideline, consensus, or standard, or from regulation. Lab has to estimate the measurement uncertainty, the non-negative parameter characterizing the dispersion of quantity being attributed to a measurement based on information used. The measurement of uncertainty shall be evaluated and compared to the criteria that has been specified before, and should be regularly reviewed. And the measurement of uncertainty do not have to be reported to the patient, but should be made available when the patient or the user asks for it. For the qualitative result that relies on the test which produce quantitative output data, measurement of uncertainty can be estimated using or shall be estimated using representative positive and negative sample. And laboratory can use ISO TS 20914 for its guideline or guidance in the measurement of uncertainty. Regarding the biological reference interval and clinical decision limit, a lab shall define the reference interval and clinical decision limit that reflect the patient served and communicated to user. Lab has to record what is the reference of this biological reference interval or clinical decision limit that it used, and also periodically reviewed, especially if they change the examination or pre-examination procedure. They have to review the biological reference interval and clinical decision limit and report it to the user or the client. We can use the manufacturer biological reference value, but it should be verified. Lab should establish IQC procedure according to specified criteria and verifies the attainment of the intended quality that ensure validity to clinical decision making. So it means that lab has to plan, to test, to monitor, review, and also do corrective action and improvement. Lab has to plan what kind of IQC material they will use, the frequency of doing IQC, and has to define what performance criteria that has to be achieved. And the testing procedure should be able to detect lot-to-lot variation. IQC should be monitored by recording that can detect trend achieved, and it should use statistical method such as the Westgard rules and Sigma rules, and also it should be reviewed periodically. Corrective actions should be done by holding, rejecting, re-evaluate result, or even re-examine the sample if there is something wrong with the IQC. And opportunity for improvement should be done also, should be established by reviewing all the achievement of the IQC procedure, whether it's still relevant to the clinical use. There is more detail on the procedure of selection of IQC material. Lab has to consider the use of, shall consider the use of the third-party IQC material as addition or alternative of the manufacturer IQC material, and regards its stability according to the test intended use, and have the matrix that is close to the patient specimen that has also commutability, and the concentration should be able to challenge the clinical use of the test and near the close to the clinical decision limit. If possible, it can also challenge the range of examination of the test. If no IQC material is available, then there is alternative for doing internal quality control to maintain the validity of the result by trend analysis of patient result, such as the patient-based statistically quality control, comparison of the result for patient sample to alternative procedure, but that have metrological traceable to the same or higher order. And the third is retesting of retained patient sample. Laboratory shall monitor its performance of examination method by comparison with result of other laboratories. In selection of the provider for the external quality assurance, laboratories should consider, to the extent possible, the provider have the effect of checking, or the scheme should have the effect of checking the pre-examination, examination, and post-examination processes. And the scheme also provides sample that mimic patient sample for clinical relevant challenge, the concentration. And it's also the scheme should be as possible to fulfill the ISO 17043 requirements. Otherwise, laboratory has to make sure that the provider are meeting the ISO 15189 requirement. In selection of the external quality assurance provider, laboratory should also consider the type of target value offered, so it can fulfill for the lab's intended use. Whether it is a consensus, reference by reference lab, or by the expert consensus, or by the lab consensus. When there is no external quality assurance provider exists, then there are other methodologies that can be used to compare lab results with other laboratories by participation in sample exchange with other laboratories, by interlaboratory comparison of the result of examination of identical IQC material. And then we compare that with the peer group of our tests. And it can also be done through the analysis of different lot number of the manufacturer calibrator, or analysis of microbiological organism in microbiological tests using split blind testing of the same sample. Comparison can also be done through the analysis of reference material considered to be commutable, and also analysis of patient sample from clinical correlation studies or cell and tissue repositories. When laboratory tests with different methods or equipment, or doing a perform test at different sites, then laboratory shall have a procedure for establishing the comparability of patient results throughout the clinically significant interval. The comparability can be done by using the patient sample, and it should be evaluated for acceptability according to the criteria that has already been defined, reviewed periodically, and when there are different identifiers, then the impact on reference interval and clinical decision limit shall be evaluated, acted upon, and the user should be informed about this difference. There are in ISO 15189/2022, the point of care testing is included and should apply its requirement. Formally, ISO 22870/2016 provided specific requirement applicable to POCT and was required to be used in conjunction with ISO 15189/2012. But with the incorporation of ISO 22870 to ISO 15189, lab-supported POCT is included in the scope of ISO 15189 accreditation, but not patient self-testing. It's not included in the accreditation requirement. And the whole ISO 15189 standards applies to POCT as for any lab-based testing. In the ISO 15189-2020, laboratory has responsibility for selection of device, training personnel, quality assurance, and also management review of complete POCT process. Lab can use ISO TS 22583 2019 for guidance in the implementation of POCT, especially for supervisors and operators of POCT. What is new in the POCT requirement? Formally, in the ISO 22870, there is no service agreement. But in 15189, in the annex, we can find that a laboratory should have service agreement between laboratory and other parts of the organization that use POCT, where the service agreement specify the respective responsibility and authorities of both parties. This service agreement may be managed by a multidisciplinary POCT committees if it's available. For every POCT test that is performed, laboratory should have clinical approval and, if possible, and when necessary, financial approval from the organization. Laboratory should appoint a person with appropriate training and experience to be responsible for POCT quality and also manage training and doing the assessment of competency of personnel performing POCT. The result from POCT should be distinguished from those reports from the central laboratory or from satellite laboratory. And users should be aware if there is difference or discrepancy between the result of different procedure or different location. What is different in the POCT internal quality control? In the ISO 22870-2016, in the manufacturer recommendation regarding minimum quality control of a specific instrument system may be accepted. But in ISO 15189-2022, IQC shall be performed at the frequency that is based on the stability, robustness, and the risk of harm to the patient. And it also in 22870-2016, the instrument-generated quality control shall be accepted, provided that regulatory authority have accepted. But in ISO 15189-2022, the laboratory shall select IQC material that is fit for its intended purpose. What about the external quality assurance? It is stated in the 7.3.7.3 that external quality assurance should also be performed for POCT testing. And comparability of examination result should be done if tests are done by different method, different equipment, or performed at different sites. So it means that laboratory that perform POCT should enroll in external quality assurance, should do method comparison between POCT instrument, and also should do method comparison between POCT and central lab. ISO 15189-2022 requirements are aligned with other ISO. In the implementation, laboratory can use all these ISO to help or to guide in the implementation of ISO 15189-2020, such as the ISO 22367, ISO 15190, and ISO 35001 for the risk identification, safety, and risk management. And also ISO 20658 for pre-analytic or pre-examination, ISO TS 20914 for measurement of uncertainty, ISO 27001 for laboratory information security, and ISO 9001 for quality management. In summary, this ISO 15189-2022 structure or format is aligned with the ISO 17025. So laboratory has to get familiar with that. More emphasis on risk management and patient welfare and safety is in the requirement of 2022 version. POCT is included in the scope of ISO 15189-2022, and all its requirements shall be applied on POCT. ISO 15189-2022 requires lab to have service agreement with the department using POCT, and it is responsible for the selection of device, training personnel, quality assurance, and management review of POCT. Thank you. Thank you,
Thank you very much. Thank you very much, Dr. Shan, for the good presentation, and it's so clear about how to fulfill and the requirement of ISO 15189. Now we continue to our second speaker, Prof. Tony Bedrick. Good morning, Prof. Tony Bedrick.
Good morning. How are you?
Are you good? How about you?
I'm well, thank you. You can see and hear me, I hope.
Okay, thank you very much that you want to give the presentation to
Yep.
us to share your knowledge. For the second speaker, can you the committee please share the CV of the Prof. Tony Bedrick? I would like to read the CV of Prof. Tony Bedrick. So Prof. Tony is going to sorry, the previous one. I would like, yes. Prof. Tony Bedrick is going to give the presentation about the importance of metrological traceability in clinical laboratories for accurate results. And now for his CV. Prof. Tony Bedrick has 2 PhD, one in quality management in healthcare, and the second is in pure maths. He was associate professor, faculty of health sciences and medicine at Bonn University for 4 years before becoming the CEO of the RCPA QAP in 2015. Now, please, I would like to welcome Prof. Tony Bedrick. The time is yours.
Thank you. I'll just put my slides up.
Yes, we can see it.
You can see them.
Yeah.
I'll just see how I can make this big. Sorry, I'm just trying to make it bigger than it is. So I just can't, I've only got a very small screen that I can see, so something's not right. I'll just go out. Can you see that?
Yes, we can.
Okay. Sorry about that. Now I
Any
apologize. I can see you now. Okay. So thank you very much for the introduction. So I'm going to talk about the importance of traceability in clinical laboratories. Now that I'll get going. And you can still see me. So what I'm going a couple of points I'll talk about. What is metrological traceability? What's the purpose of it? Why is it important? How can you claim that your laboratory measurement is traceable? I think that will be what a lot of people will be interested in, and the implementation of traceability in the laboratory. So I think there's two key concepts that we need to understand, both linked, particularly in the implementation of traceability. One is actually the definition of traceability itself. So metrological traceability is the property of a measurement whereby the result can be related through a reference material through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So basically what it means is that when you measure something in your laboratory, you have come up with a measurement for a patient result, that you can track that measurement result back to a calibrator that's been provided for your analyzer, and back to a master calibrator that's been provided by that manufacturer to a whole lot of analyzers like yours, back to again a master calibrator within that organization that they use to calibrate all their calibrators, and then back to where they got that calibration value from, and hopefully that hierarchy would go all the way back to a pure substance for the material that you're trying to measure, being measured in a definitive method, or a method with very, very high accuracy. So that's what traceability means. It means that you can basically say that the result that I'm giving my patient or your patient for this measurand based on this instrument, that in fact I know that the calibrator value that allowed me to determine what the patient value is can be traceable back to a master reference material and using a reference method. The other key aspect is, or key concept is commutability. Commutability means that the material, be it a calibrator that you use on your instrument, QC material or EQA material, behaves in the same way that a patient sample does. And the reason why it might not is that often to make the calibrator or the QC or the EQA material, we need to go through a series of steps just to ensure that the material is stable. And also that there are a range of concentrations in that material that would be suitable for you to be able to determine in your assay with QC or with EQA that there's a problem at either the high concentrations or at low concentrations. So to create those materials, the manufacturers normally will take some pooled human serum, and then they may filter it to remove some molecules, so you get low values. They may then spike the material with high values so you can get the high concentrations. Then to make it stable, they'll add some preservative, maybe some antibiotics, and then lyophilize the material. So by the time all those steps have been gone through with the material, it's quite possible that for some measurands, it might not be commutable. It's also quite likely that for a lot of measurands, it will still be commutable, but it's hard to prove that sometimes. So meteorological traceability can be characterized by the following essential elements: that the measurement must be defined initially. So what you're trying to measure, if you're trying to measure sodium, that you've defined what that sodium is. So it's the element sodium. It's in serum, and it's measured in terms of millimoles per liter of sodium. There's then this unbroken chain, which I will show you, of measurement system and calibrator. Based in the case of sodium, it may be a pure sodium sample that's been weighed out in terms of the weight, so you know exactly how many millimoles of sodium there are in that calibrator, and then you measure it in a very accurate system, some sort of tandem mass spec system, so you've got a very high quality measurement. And then from then on, you start to produce other calibrators that are used eventually by manufacturers, and then they produce other calibrators that are eventually used on your instrument. There's a documented calibration program where all these calibrations are established and repeated. There's documented measurement uncertainty for each step. Each time you measure and you move to the next step where you then create a calibrator based on the previous calibrator, you introduce some error. So as you go down this calibration chain, there is more and more error introduced because of errors in the measurement process, no matter how good the system of measurement is, and also in the actual process of making calibrators. And then there's a documented measurement procedures, etc. So that's all part of this calibration chain. And you can see here exactly what I've been talking about, this hierarchy, starting off with a primary reference material. In the case of sodium, it'll be, solid, high quality, sodium something or other, sodium chloride perhaps, then measured in a primary reference method, probably mass spec, and then that in turn produces another calibrator, which will be not quite as high quality, but then measured in a secondary reference method, maybe not quite as good a method, but that will then produce a manufacturer's calibrator, and they will then, using this calibration material that they've produced themselves, usually in very high volume, because they want to have standard calibration for a long period of time. They'll have an assigned value by this secondary reference method, etc., all the way down to you in your laboratory with your patient sample. And this is what traceability is about. To put this system into place, you need a whole series of requirements. You need these very high purity reference materials. And I say in the case of sodium, it will be a dry solid, high quality dry solid with no low levels of hydration, but pure standard. You'll need a reference method procedure such as tandem mass spec, a network of laboratories that are specialized to do these sort of high level calibrations. They're usually the national metrology institutes in each country. To interpret the results, you still need high quality reference intervals. You need EQA schemes, because it's only with an EQA scheme that you can actually tell that these different methods are used by manufacturers, which in turn may have different hierarchies schemes to produce the different traceable hierarchies to produce their calibration materials. Only with EQA, where you send out a sample, that you can see that in fact different methods with different hierarchy traceability chains actually have give the same result. You also need laboratory accreditation to ensure that that traceability is also being put into place in these laboratories, and that's what I'll talk about later. You need regulators who will go around and assess laboratories against these standards, and of course you need manufacturers part of this process, because they're the people who need to use their own calibration processes to ensure that there are traceable steps in place, and that's the role of EQA there. So again, I'll keep moving on now to why do we want to do this? And this is obvious. Currently with lots of processes that we have, different analyzers, different calibrators on different analyzers, different reagents sometimes even will produce different results. So you want to move from this process where different analyzers with the same patient sample will give different results to some sort of process where you can harmonize those results and come out with the same result on the same patient sample for the same measurand when bled at the same time. That sounds good, but the problem with that simple process is that in fact there's many variables that contribute to differences between laboratory results. The manufacturer's product calibrator might not in fact be traceable to a higher order reference material. The laboratory reference routine measurement procedure might have problems in it. There may be errors because of that, how the actual laboratory processes work, and that's why you need external assessment of laboratories. Reagents, some laboratories may use reagents from a different manufacturer that don't actually give you the same result that the manufacturer's calibrator would give you in their instrument, and the instrumentation used itself may not be of a high quality. So again, this is the full top-down traceability that I mentioned before, and that's what we're aiming to have. For that to work, you need at the top of the hierarchy, you need this certified reference material, this very high quality, very pure, very well-defined calibration material, reference material. And you also need a very high quality method of determining what the material of interest is in that material. So you need a high quality reference material and a high quality reference method. And if you go to JCTLM, and JCTLM is the Joint Committee on Traceability in Laboratory Medicine, they have a website where they hold, as for our profession, they hold all the reference materials that are available, the certified reference materials that are available, a list of all of those, a list of all of the certified reference methods that are available, and they're all of these have been verified by the JCTLM, and also all those reference laboratories that can use both of those to produce a high value calibration. This is from their database fairly recently, and you'll see that there's quite a few of reference materials and reference methods and reference laboratories available. But in fact, despite that, and then they cover about 180 measurands, but in fact, you know that we measure a lot more things in laboratories than 180 measurands. So there are, in fact, many measurands that are not in the standardization process, in the hierarchy. And that's because there either isn't a reference method, because we measure a lot of our measurands by antibody methods, and they're not specific or sensitive. And there might not be reference materials available either. There might not be certified reference materials, particularly for measurands like hormones and antibodies. You know, we don't have pure reference materials that we can use to calibrate our processes. So I'll just divert a little bit now and talk about EQA. And I say EQA is critical in this whole process because it's the way that we can assess whether or not laboratories and therefore manufacturers' methods are producing results that are traceable. So what in a laboratory, what people want to know is my laboratory following the manufacturer's guidelines for my method? That's really what you want to know. Is my lab, when I look at my EQA results, what I want to know is my laboratory getting the same results as other people using my method, my manufacturer's method and reagent and calibrator? Because that's the way you are assured that, in fact, you're using that method appropriately. So am I getting the same results as everybody else using this method? You may also get from an EQA scheme, you know, is the method linear? Am I getting good results for high and low results? And that can be particularly important in assays where there could be antibodies and you could get, excess of antibody or antigen. EQA is a quality improvement exercise. So if there's a problem found, you go through a process of trying to identify what the problem is. And in many EQA schemes, you can also assess whether or not the assay is subject to interference from hemolysis or lipemia or other drugs. The EQA audience may also be an accrediting agency. So this is the agents that we mentioned, one of the pillars of traceability. These are the organizations that come round and ensure that laboratories are performing the way that they should in terms of using the best methods that are available to that laboratory and using them usually by oversight of EQA to see that, in fact, they're getting the same result as other people using their method, to ensure that they're using QC appropriately to make sure that the method works, and that the operators are properly trained, etc. So what accrediting agencies want to really see is the laboratory performing as well as it should, given the methods that it's got. But if you've got methods where, in fact, there's no higher reference material, there's no certified reference material because of those reasons I mentioned before, we don't have a pure material, or if there's no certified reference methods such that they don't measure what we measure accurately, and as I said, antibodies are one example of that. All you can do is have this very limited traceability chain, and that is that for your patient results, the best you can hope for is that you get the same result as other manufacturers, other laboratories using the same instrument and reagents as you are. So the best you can hope for is that you get the same result as other people using your method. And that sounds all right, because say that's what laboratories often look for. So as long as I get the same answers as my peers, I'm pretty happy. So is that okay? But let's think about that. How do clinicians interpret a result? So we in the laboratory we produce a result, and we get the same result as other people using our instrument and our reagents. So that's good. The result goes out. How do clinicians interpret a result? Well, there are a number of ways clinician can interpret a result. They have to compare it against something. You know, you can't look at a number and say it's 25, and without any comparison to some sort of benchmark, you don't know what that means. So what are the benchmarks you can use? Well, you could use a reference interval, a normal range. So is 25 within the reference interval, or if not, is it outside? So that tells you something. I can interpret, therefore, that when I look at my patient in terms of the reference interval that's been calculated using a reference population, the patient is in or outside that reference interval. I can use a decision point. So there might be for many, and there are for a number of measurands, there are critical decision points, you know, since for the diagnosis of diabetes or pregnancy or hepatitis B, if the measurand exceeds a certain set point, a certain clinical decision point, the patient is diagnosed or could be diagnosed with something. I can, if I'm looking at a patient results over time, I can see that the patient's results are getting better or worse, you know, based on treatment or the progression of the disease. So I can look at previous results. Or sometimes it's just the analysis, the interpretation is based on the physician's experience. So the physician will say, you know, I've seen this before, I've seen this change in results before in other patients that I've had, and I know that it means that the patient's getting better or worse. So I'll just show you some results now that hopefully will bring some of these concepts together. So this is results from an EQA scheme. It's for ferritin. And you can see in the top left and right hand, there's a series of histograms, and they represent for two samples that were in this EQA scheme, two samples that went out to a whole series of laboratories. You can see the spread of results in those histograms up there. There's a ferritin that's got a median value of 207, and another that's got a median value on the right of 17. So so you can see where those arrows I've just put, you can see that's what this laboratory got for those two samples. And you can see that on the low sample that the laboratory got, you know, right in the middle of the acceptable range, which is in the white area, and on the high value, which was 207, they're just on the edge of acceptability. But when you look at that, particularly the left-hand diagram, the histogram, you can see that there's a very broad spread of results. And in fact, there are a lot of results that are above the acceptable limits and a lot of results that are below the acceptable limits. It's also apparent with the low value, the median value of 17, you can see there are a number of labs that got lower results than what was deemed to be acceptable. This is for this laboratory. This particular laboratory was using Abbott reagents. You can see that all the results of the people using the Abbott reagent and on the architect are inside that box, and you might just be able to see that there's an X where this particular laboratory is, and you can see that the laboratories actually perform quite well against their peer group. They've got the same result as most other people who use their method. But you can see if you look at all those labs that are using immunochemiluminescent methods, that there's another group of laboratories, another method that in fact have got low results for this same sample. And you can see it more clearly here on the left-hand Uden plot, where I've circled the blue and the red. You can see there are two populations for this ferritin assay. So two different manufacturers in this case who have got really quite different results for the same EQA sample. We often think, well, this is a problem with EQA material. It relates to the commutability issue that I just mentioned before, that in fact, during the process of making this ferritin material, you know, they've either used a different spike of ferritin, and that's why, you know, there's a different result for different methods. The ferritin method is an antibody immunochemiluminescent luminetic method. So you can imagine there's antibodies, so perhaps the antibody reacts differently to whatever they use to spike the ferritin in this sample. This is, in fact, this EQA program also provides probably, most likely, a commutable material. It's a sample that's been taken from a patient that's been bled because they've got hemochromatosis. So that this is a phlebotomy sample, and you can see that, in fact, if you look at the results, you can now, in green and blue, you can see for this patient, which to all intents and purposes is commutable, you can see that there are two completely different populations on this one level. It's the level of ferritin so there's two levels. There's a high level and a low level, but you can see that there's really three populations. There's a population in green that got a high value, population in blue that got a low value for this same sample, and then there's a group in the middle. If you look over to the right, where the numbers are, I've highlighted the numbers. You can see that for the Roche diagnostics method on this patient sample, the range of values was between 37 and 49 for the low value, and 229 to 309 for the high value. And if you look, for example, at the ortho clinical diagnostics method, the result for the low value was 16 to 24, and for the high was 122 to 164. So those two methods, the patient results, the methods from different laboratories using those two different methods didn't even overlap. Okay, so those, depending where you went, if you were a patient and had your assay, had your sample measured, if you had it on these two different methods, you would get completely different results, as you can see there. So what? Well, why? With ferritin, it's one of those assays where, in fact, we use a clinical cutoff, a decision point to define whether or not you've got some disease, be it iron overload or iron deficiency, and the cutoff is less than 15. So most clinicians would use from experience that, in fact, the cutoff for iron deficiency is less than 15. On this assay, if you use the Roche assay, you would get a different result to if you use the ortho assay or those other assays. So here's a problem where, because there is not traceability in the assay, and people are using a cutoff, a generally accepted cutoff, people will be misdiagnosed unless that laboratory is very careful and they have a different cutoff for iron deficiency and a different reference interval, etc. And this just is more data showing the same thing for different assays for ferritin. Based on the assay, because there is not traceability within the assay, you can get the wrong result. You can get a different result based on the assay, but using the same cutoff, you will be misclassified. It's not just for ferritin. There's a whole lot of assays like this. This shows albumin, depending whether or not you use an immunoturbidimetric method or a colorimetric method. This albumin was very important during COVID as an indicator of poor prognosis. And you can see that there is separation between those non-survivors and survivors if they use an immunoturbidimetric method, not so with colorimetry. So again, it makes a difference. This is HbA1c, and again, this is EQA results. And you can see for these are in fact commutable samples. They're patient samples, whole blood samples. You can see that here that there are two methods that give different results to all the other HbA1c methods. So again, these patients would be misdiagnosed if with the cutoff that we currently use for the diagnosis of diabetes. So the problems with non-commutable EQA are that you might not detect significant errors, or you will say, well, this is a problem with the material, not with, in fact, the assay. But in fact, you need to be very careful that, in fact, you don't discard EQA results, because, in fact, they may well be telling you something. But it doesn't matter, really. You need to see that if you have non-traceable results, non-traceable assays, you may end up misdiagnosing a patient if you use a set cutoff or a set reference interval. So these particularly where there's clinical decision points, you rely on the manufacturer providing traceability. So that's why it was important. I'll just show you some other examples where, in fact, I talked about harmonisation. Clearly, what we may have to do in certain situations where there are different results coming out on the same sample, the same patient sample, on different methods because there's not traceability, we need to try and do something to ensure that those results on the same patient on different assays end up being not clinically affecting the patient. So here's some other examples where you may in fact get movement in results. It could be a calibrator change. So this is an example of alpha-1 antitrypsin where in fact the calibrator was changed in the assay and it introduced a significant bias. You might have two different instruments in a network or even in a hospital where in this case there was a point of care device and a mainframe assay, and there was a 24% difference in patient results. So this happens all the time in hospitals. Or this is where there were two different methods for lipase in different laboratories that were in the same network, and there was a 33% difference in the results. So this is situations where, again, we need to ensure that there clearly isn't traceability. In one, the calibrator changed. Another one, there were two assays, or another two, there were two assays. So this problem arises all the time. So what we need to be able to do is to in those situations where we know our hospital or our network is producing different results on the same patient because of different methods, we need to apply a factor to make sure that those results are in fact don't lead to clinically poor outcomes. So there was a paper there that I mentioned, and that just is a way that you can add factors or create factors that will overcome this problem. The other thing I said that, when you interpret results as well as decision points, you might use reference intervals, and more laboratories or countries are trying to use common reference intervals because there's obvious advantages in doing that. If you have, no matter which laboratory you get results from, if you're a clinician, if the same reference intervals apply, that's got to make it safer for patients everywhere. And a key role of EQAs is to in fact ensure that if you are using common reference intervals, that's valid, in that the instruments that are producing results, they don't change calibration, and therefore they don't change the results of patients over time. So you might have decided at some time we're going to have a common reference interval for sodium or glucose. You want to ensure that once you've done that work, that at some time down the track, at some stage down the track, that there hasn't been a calibration change or a method change to a particular method, so that the results are no longer comparable and you can't use a common reference interval. That's another issue that we have. You saw with the alpha-1 antitrypsin, because of a calibrator change within a laboratory, that clearly the results change. So that would have meant that they were no longer interpretable using that same reference interval. You need to ensure that your reference interval is still valid for results. And this was just some work that we did at the EQA, the QAP, and that we tried to see if in fact you could use a common reference interval for a whole lot of measurands, and we found that you could not at that point in time. That's just more data that shows the same. So I posed the question. We know this diagram from Plebani's work, and what it says is that basically very few errors occur in laboratories now because within the analytical phase, because we do that so well. I'd question that because of what I've just said. In fact, we might produce the same results within a method, but in fact, different methods produce different results. To me, that's an analytical problem, and therefore patients will be misclassified. And ferritin is a case, where we try and diagnose iron deficiency, and if you're using a different method with the same cutoff to everybody else, it may well be that you're misdiagnosing a whole lot of patients. So there's the lack of traceability of assays creates a whole lot of problems for patients. I think we're deluding ourselves. I think we don't have as much control over analytical error as we would like. So how can you ensure that you've got traceability in your laboratory? And this is where ISO 15189 comes into play. There are requirements under 15189, that the laboratory needs to show that wherever possible that they're aware of any higher order reference materials that are used in their methods, and similarly reference measurement procedures, the calibration hierarchy. They need to understand what measurement uncertainty is associated with the calibrator that they're actually using in their laboratory, and they need to see what those uncertainty limits are compared with what they think is acceptable. And this just shows that this is for a simple assay. This is for glucose, and different manufacturers, there's 4 of them there, and on different instruments we'll use different hierarchy chains. Okay, this is to try and show, this is manufacturers demonstrating that they've got a traceable result for glucose, and you can see here that for 4 manufacturers, and in fact within a particular manufacturer, there are different reference materials, cited, SRM 965 or 917, different higher order reference methods, IDMS or enzymatic or not declared, and here different traceability chains. So even for something as simple as glucose, there are different traceability chains, which is highly likely to mean that even though you've got a traceable assay, you will get different results from different traceability chains. This is from NATA. NATA is the National Association of Testing Authorities. It's the Australian assessment agency that goes into laboratories and assesses their performance against 15189. This is what they provided to ensure that, in fact, laboratories meet the requirements of 15189 for metrological traceability. So I'll go through these in some detail, so don't get worried. So you need to start at the top, and you need to show that you've got appropriate equipment. This is for traceability, reference materials and measurement standards, consumables and procedures. So firstly, was the component controlled through calibration during validation and verification? They call it VQ. So this is to ensure that you meet in your laboratory the requirements of 15189. Okay, so firstly, was the component controlled through calibration? Does this component have values specified in a measurement process that are critical to the result? Again, I'll go through these in more detail. This is just the questions you need to ask. Does the component, this is what we're measuring, contribute directly or indirectly to the units of the reported result? Is there a procedure, a reference measurement procedure, or an accepted consensus standard? Is this component a reference material or measurement standard? If the answer to any of these questions is yes, then you must establish evidence of traceability for the component to be a stated reference appropriate to the component and measurement task. If the answer is no, then traceability is not essential for the component. Okay, so let's now go through a couple of examples and just to try and translate those requirements into something that your lab will need to do. So let's start off with a chemistry situation first of all. So this is an analyzer that's measuring enzyme activity, and we assume that that there's a reference. The reference method would use, in fact, an IACC reference procedure, and of course the analyzer we assume is following Beer's law. So while the IACC offers reference materials for some enzymes, they are mostly used by equipment manufacturers to validate their method. For this example, no calibrator is used, and that's because you're looking at a change in absorbance at a particular wavelength. The autoanalyzer is seen to be a standard method, a black box standard, and the result is reported in units per volume. The components that are used in this measurement procedure are really the autoanalyzer and the reagents. So in terms of the autoanalyzer, in this case, the results are traceable to a standard method, which is comparable between results, and the standard method for enzymes is this change in molar in absorbance based on measurement of absorbance by the sample and then multiplication by a molar extinction coefficient. So for that to work, you must assume that the autoanalyzer is functioning correctly. So you need to demonstrate in terms of traceability that the analyzer is maintained appropriately and that frequent calibrations occur. The manufacturer needs to show that they validated the method against the IFC methods and using a certified reference material if possible. And again, the evidence that you need to show are things like the installation and commissioning records, routine maintenance, satisfactory EQA results, and QC showing that the method has got good statistical control. And the reagents aren't so important because reagents in use are important, but not to the source of the traceability itself. So the reported result, this process is traceable to the IFCC method or CRM. If we look at, again, another example here we're looking at measuring an analyte that's not an enzyme. So here, calibrators and reagents become more important because we're not measuring just a change in absorbance, but we need to have the reagents as part of the assay. So again, the same sort of thing happens for the autoanalyzer as before. We just need to show, in terms of traceability, we need to show that that component, the autoanalyzer, is in fact, as we saw before, that it was commissioned appropriately, it has regular routine maintenance and satisfactory QC and EQA performance. The calibrator, we need to ensure that the calibrator contribute to the units in the final report, and that they are generally there's a reference material of some kind that is calibrated in terms of millimoles per litre or whatever. So we need to show that the calibrators are traceable where possible back to a CRM or at least to the manufacturer's certified material. In terms of the reagent, there's no question the reagents in use are important, but are not a source of traceability. It is noted that lot-to-lot variation may affect the results, so the quality of reagents must be monitored. So here, in terms of meeting the requirements of ISO 15189, the same sorts of things apply as earlier to the autoanalyzer itself. That's the black box. We need to show that it's been commissioned appropriately, it's been maintained appropriately, and a satisfactory EQA and QC. With the calibrator, we need to show that there's traceability in the calibrator to a higher reference material, or at least back to the manufacturer's reference material. We can't be using our own calibrator. And the reagents, we really need to just check that there's no significant lot-to-lot variation, which is a different process. So again, the result of this process is traceable to a standard reference method. If we look at something like isolation of bacteria, again, the components this time are the agar plates, the incubator, the control organism, and the method. So just going through those same steps, we need to ensure that the agar plates are quality controlled. For the control organism here is the reference material. So therefore, traceability is required for these organisms to show that, in fact, that they've been stored appropriately, and that there's some sort of traceability back to ensure that you've subcultured that primary strain appropriately, and it hasn't changed characteristics over time. In terms of the incubator, which is sort of like part of the analyzer, you need to ensure that there's optimal temperature growth, and that the incubator is kept well maintained and calibrated. So that meets that requirement. And the method is it's a standard or consensus method for growth, and that you need to demonstrate comparability of results with identification of other organisms, etc. So again, you can see that if you go back to the original flow chart, you just need to go through those steps, see what the sort of the analyzer is, what the reference material might be, the impact of the reagents, and the impact of the method itself. And this is just one final example, and this is immunoanalyzer method. Here are the components are the plate reader, the calibrator, method, incubator, and reagent. So the plate reader, really, there isn't much there except to ensure that it's functioning appropriately, that it's been maintained and serviced, and that the manufacturer has assessed that it's working appropriately. The calibrator is important for immunoanalyzer assays, so because the calibrators contain what the units are. So they're reference materials. So these calibrators must be traceable back to a higher order. It's usually not possible with ELISA, but you need to trace them back to the manufacturer's calibrator values. So you can't be seen to be using your own calibrators unless you've got some traceability back to another standard. And the method process is really a consensus method for a value, for an analyte, sorry. So those questions are relatively easy to answer. The incubator, again, the same sorts of things apply as before. You need to ensure that the equipment is providing, the incubator is providing the optimal temperature, that it's been well maintained, and that temperature is calibrated. And the kit, really, the kits are important, but the traceability isn't involved with the kit. You only just need to ensure that there's not lot-to-lot variation between kits. So the reported result of the process is traceable to the traceability of a measurement result in the laboratory is achieved by use of certified equipment, that the equipment is calibrated, staff are trained and competent to use those measurements, and that there are documented procedures and calibration and calculation processes in place. So in summary, lack of traceability is a risk to patient safety, and you saw that with those common examples where, because there's no traceability for some assays, different manufacturers will produce assays, that will produce different results that, if they're interpreted using a cutoff point, a cutoff decision level, or even a reference interval, patients will be misclassified. So laboratories need to understand what this means to their assays. You need to understand that while it's great to get the same result as everybody else using your method, you need to ensure that there's an appropriate reference interval or an appropriate set of decision points for your assay, because clinicians will use, based on their experience, decision points or reference intervals from what they're used to using. There's a process that I've shown, and that references to available on the web if you want to get that NADA reference. That will assist you in meeting the requirements of 15.189 to demonstrate the traceability of your assay. Factors, results change, calibrators will change, assays will change over time because of changes in calibration or reagent lots. So you need to be aware that sometimes you may have to factor your results to make sure that patient results are consistent over time. And that's my talk. Thank you very much. Thank you.
Thank you very much, Prof. Tony Bedrick, for the clear and good presentation and the discussion about what is the metrological traceability, what is the purpose, why the traceability is important to the clinical lab, and how can you claim the lab is traceable, and the implementation with the examples that you give to us. And for the participant, that if you would like to ask questions to Prof. Tony Bedrick, please ask in the Q&A and write the question is asked to whom. If it is for Prof. Tony Bedrick, then please write down it's for Prof. Tony Bedrick. Now we continue to our third speaker. The third speaker will give the presentation about the uncertainty of measurement in clinical laboratory as a tool for improving the result interpretation by Prof. Ken Sikaris. Can you please display the Prof. Ken Sikaris CV? Okay, Prof. Ken Sikaris is a University of Melbourne graduates. Prof. Sikaris trained at the Royal Melbourne, Queen Victoria, Prince Henry's, and Heidelberg Repatriation Hospitals. He obtained fellowships from the Royal College of Pathologists of Australasia, RCPA, and the Australasian Association of Clinical Biochemists, AACB, in 1992 and 1997, respectively. Please, Prof. Ken Sikaris, the time is yours.
Thank you. I'll just share my slides. So you can see the slides?
Yes, we can see.
Good, thank you. Well, thank you for inviting me to give this talk. It's been a while since I've been to Indonesia. I wish I could be there, but it's nice to speak to all my colleagues in Indonesia. The topic is an interesting one. I'm very glad that Tony's given you this background of uncertainty, and that we also had the topic of ISO 15189, because we really continue on that theme of technical requirements and accreditation. So what I'll be discussing in my talk, our third talk this morning, is what is uncertainty of measurement? How do you calculate it? How do you report it? What does it mean? How would you use it in interpreting laboratory reports? And how often should you review? So we'll cover all of these things. So starting off, what is measurement uncertainty? Well, essentially, the term was invented in 1995 by the ISO GUM, the Guide to Uncertainty of Measurement. And the International Federation of Clinical Chemistry and Laboratory Medicine, which the Indonesian Association, APFCB, belonged to, they agreed to this form of describing the quality of our measurements. Now, there is an update in 2008 of the guide, but it hasn't really changed significantly. So one thing to say is that we're used to the terms of imprecision or bias or inaccuracy. Those terms still exist, but they're only one of the forms of the overall uncertainty in the measurement. So those terms haven't disappeared. They're only part of the concept of measurement uncertainty. So this idea that, there is a true result for any measurement, but imprecision will cause us to scatter around that result. Bias would cause us to always miss the result. And then you can have a mixture of imprecision. They're all covered on uncertainty because we're not sure what result we're going to get with relation to the true result. So the term uncertainty means the doubt about the validity. But measurement uncertainty means the doubt around a measurement, and it really applies to quantitative results. Now, there's a lot of uncertainty in laboratory medicine. There's uncertainty about whether we bled the right patient, whether the sample was taken properly, whether the report was delivered properly. They're all part of uncertainty, but they're not part of measurement uncertainty. Measurement uncertainty really is just confined to this concept of the analysis, the measurement. So distinguish lab uncertainty as a subset of overall laboratory uncertainty. Now, both ISO 15189 describes the importance of uncertainty, and there is another standard, 2019-20914, which is the standard for measurement uncertainty. So it provides a bit more detail that 15189 doesn't have, and I'll be referring to both of those documents during this talk. So according to 15189, measurement uncertainty is a non-negative parameter, it's a number, that characterizes the dispersion, the spread of results that attributed to a measurand. So it means when you measure something, you'll get a whole lot of different results, and the measurement uncertainty describes how much that spread is in a very standardized way. So what can cause measurement uncertainty? Well, as Tony was saying, the calibration process can cause uncertainty, primary, secondary, tertiary calibrators. The instruments, the environment, the electrical supply, the water supply, the lot-to-lot variability of reagents, the individual scientists and the way that they personally prefer to handle their pipettes. All of those things, they all cause a scatter in the results and uncertainty. So really uncertainty is the sum of all of the things that are involved in analysis. And we know that when we've got random sources of variation, they tend to follow this Gaussian distribution, which I hope everyone's familiar with. There's a mean and a standard deviation, and 95% of results lie within 2 standard deviations. So that's what typical uncertainty looks like. And it's because there are so many things that cause a result to deviate from the ideal. And so in the Guide to Measurement Uncertainty, they describe that curve. The mean is the center of the curve. So that's presumed to be the ideal result. The SD, which is also called the standard uncertainty, or the standard routine uncertainty, because that's what you get when you measure things over and over again in the routine laboratory. And then there's another concept, which is the expanded uncertainty, and that's the total spread rather than just the SD, or the standard uncertainty. There's the expanded uncertainty, which is the mean plus or minus 2 SDs. So here the coverage factor is 2 SDs. So the expanded uncertainty tells you how many SDs of spread you're describing. And really, it's a standard, in healthcare and statistics, that 95% confidence is what we want to portray. So how do we calculate it? Again, 15.189 provides a guide. There are 2 methods, type A evaluation and type B evaluation, and they're slightly different. Of course, all of them involved repeated measurements, but they're slightly different in their approach. So type A, which is in GUM described as by basic statistical methods, so by a really basic statistical understanding, and type B is by something else. Now, something else is not statistical. It's just something which isn't fundamentally statistical. It's something which is a broader statistical description. And it also can be considered a total error approach. So in type A, all of those things that I said, what is the uncertainty of the balances that you use to set up your reagents? What is the uncertainty of your pipettes? There's an uncertainty of flasks. There's an uncertainty in your calibration curve, the standard error of the line of best fit. There's uncertainties right throughout the process. So typically in a fundamental statistical approach, you would sum up each of these components and sum them together. And when we sum uncertainties, we do the square root of the sum of the squares. And then we can define. Now, in reality, no laboratory does this. It's a great purist approach, but it will take months, at least months, to do this for any method. And we have done this in our laboratory before, mainly for manual methods like mass spectrometry, where you do know the precision of your balances and the precision of your flasks and everything. But really, it's foreign. Most people do not use type A methodology. Most people use type B. And type B is described in GUM as the experience with or general knowledge of behaviour. So an overall view of all of those things that contribute to the uncertainty of measurement. So where do we get that overall view? That overall view comes from IQC material. When you're running a QC, it's the sum of all the variations. The pipette errors, the day-to-day variation in the machines, in the environment, the different staff that you're using. The QC is the sum of all of those things without knowing them individually. There is another uncertainty which I'll be returning to, which Tony has covered for you, is this uncertainty of the calibrator. I'll come back to that point. So that's part of the type B evaluation. So as I said, when we run QC, we'll get a scattering of values. We can calculate the SD, and we know the SD of our measurement through the use of QC material. So the SD of our QC is the standard uncertainty of our method, and the 2 SD limits of our QC is the expanded uncertainty of the method with a coverage factor of 2. So it's the same thing. So in the uncertainty guide, precision under repeatability decisions is considered that uncertainty. And then within laboratory precision for a sufficient period is called the long-term precision. Because in a way, when you first get a method and you run it 20 times, well, you haven't checked how much a different analyst might cause the method to vary. You haven't measured whether a new lot of reagent might cause it to vary. You haven't caused whether a calibrator shift may cause throughout vary. So the initial assessment is just an initial assessment, just to see whether the method's working as you expect. But the long-term uncertainty of your QC is the overall uncertainty of everything that's happening in the laboratory. And the longer term it is, the more it's capturing all of the different reagent lots, all the different calibrators, and all the different analysts. So the longer you run this, the more confidence you have that your QC SD is your measurement uncertainty. So now this is a European manufacturing sort of definition. So when you do that, they say that your uncertainty, now this part here, the uncertainty of the sample, we're saying that's not measurement uncertainty. Whether they collected into EDTA or didn't fill the tube and everything, that's a separate problem. But really, in terms of measurement uncertainty, we've got the method, that QC, and they say that you must consider the calibrator. So the manufacturer has given you a calibrator, and that calibrator has an uncertainty. So have you included the calibrator uncertainty in your long-term QC? You can only say you've included the calibrator uncertainty in your long-term QC if you've run the calibrator many times in your long-term QC. Now, what does many times mean is a very interesting question, which I'll return to. But really, you should consider whether you've included the change in the calibrator, which may come in the future, that the manufacturers warned you about, in that statement of uncertainty, because it is a part of the process that you're uncertain about. So, and in the 20914 standard, it does describe this importance of the uncertainty of calibrator. And it goes on to say that, you know, the manufacturers, when they give you a calibrator, have to provide the uncertainty of the calibrator, because otherwise you don't know how this method might change in the future when the calibrator shifts slightly. So here's an example where they say that the calibrator has an uncertainty of 0.5 over, which is 0.027 or 2.7%. Now your internal QC has an uncertainty of 2.8%. So that if you add both of those up, 2.7% for the calibrator and 2.8% for the uncertainty, using the square root of the sum of the squares, you'll get a 3.9% uncertainty. So really your uncertainty is both your QC and the manufacturers told you that the calibrator may vary. So the expanded uncertainty is twice that value, so 7.8%. So it's an important thing to consider whether you've included that. Another thing to conclude there, now we're going to cover goals of uncertainty, analytical goals soon, but let's say for the creatinine method, our goal is 4.5% CV, and they've told us that the calibrator has an uncertainty of 2.1%. Well, it gives us room for the method uncertainty. But with sodium, typically, our calibrator has an uncertainty of 0.84%, but our goal is 0.5%. So in a way, the manufacturer's already used up the entire error budget in their calibration. So it's one of the reasons why it's very hard to achieve analytical goals for something like sodium. It's hard enough to achieve it in the laboratory, and it's compounded by the fact that your calibrator may vary by even more than your goal. So just things to consider there. You must keep it in mind. So as I said, when you initially get an assay in your method validation, when you first get a new assay, you'll do a within-run CV. You'll run it several times on one day, and then you might run it over 10 days and get a between-run CV. That's your initial uncertainty estimate. But it's important to get a long-term estimate of uncertainty by running that QC, well, ideally over many reagent lots, over many calibrator lots, using many analysts. And if patients go to different machines, even considering whether the uncertainty should be calculated across machines. And I'm not going to go into that detail, but I'm happy to answer questions on that. And this is an example of, this is our uncertainty sheet for Melbourne pathology for the Cobas 8000, our general chemistry analytes. And we've got uncertainty measures for each line. So if I zoom in on this, for the albumin assay, the low QC has got a value of 26. We've calculated the QC variation as 0.4. So the CV is around 1.5%. It's 1.5% on line A, but 1.8% on line C, 1.8% on line. So it's a question that you need to answer for yourselves at this stage, whether the uncertainty is the uncertainty on a particular machine or the uncertainty is the uncertainty across all machines. But anyway, we provide this information for whoever might ask for it. And this is a paper by Mario Plebani and group who was saying, now they were saying something different. They're saying, why do you have to use internal QC, long-term internal QC? Why can't we use EQA? Now, some EQAs, like the ones that Tony showed you, do have repeated samples, and they can work out whether your repeats are they can calculate the uncertainty of your EQA submission and provide a CV. Now, which CV is better? In a way, this is an objective CV. It's not produced by your laboratory, it's produced by an EQA provider. So maybe this is a better estimate of your CV than your internal QC. Well, let's delve into that. What's the difference between EQA and internal QC if we were going to use them to estimate uncertainty? Now, neither material is patient material. So that's a handicap for both. But anyway, let's say they're identical from that handicap. EQA can have many levels. Over a year, you might get 10 different levels of EQA, but internal QC, you might only have your low and high QC. So in a way, EQA is a bit of an advantage because it looks at your uncertainty over many levels rather than over one or two levels. So there's a point in favour of EQA. The analytical range is usually very wide because EQA often provides pathological results, whereas usually the high and low QC at the top and bottom of the reference interval. So again, there's an advantage to the to EQA. What about the number of measurements? You might submit 16 results for your EQA, but over the same period of a year, you might have hundreds or thousands of internal QC results. So the higher the N value, the better the estimate of your SD. So there's a big advantage to internal QC, the number of measurements that's developed that standard deviation. The other thing is that you could run your IQC over years, so there's a bit of an advantage there rather than EQA really just runs over a set period. Bias, well, now bias is estimated in external QA, whereas you might not understand whether you've got a bias compared to the traceable method and if you're just using internal QC. And then outliers. Now, when you're running internal QC and you see an outlier that you've got an explanation for, you'll remove it from the statistic. But in EQA, depending on the EQA program, outliers may not be excluded. And so what happens there, and in this sort of study that we did, we compared the CV that we'd get from internal QC for each method compared to the QC that we're getting from external QA. And you can see that generally they agree. They're generally close to the Y equals X line. But here are some outliers for EQA. And the outliers for EQA tend to be because there was an outlier in the EQA which wasn't excluded from the statistic. So really the issues of outliers and the issues of the N values are the big difference, is why you should be using internal QC rather than external QA for your measurement uncertainty. And that's said in the GUM. They said type B evaluation can be better than even the purest type A evaluation, especially when type A evaluation is based on a small number. So they're saying that a large number it tends to be the better measurement uncertainty. So what is a large number? What N value do you need to provide a reliable estimate of CV? So you can do this in a spreadsheet for yourself if you like. This is a random sort of analysis of, this is a method that had a true CV of 5%. Now, when we take 3 results from that method, we usually underestimate the CV. And the way to understand that is, if we've only done it 3 times, we haven't given it a chance to spread as far as it normally would. So the small N value gives not only an underestimate of the CV, but those 3 results could give you a CV of 0 because they just happen to be exactly the same, or they could give you a CV of 7% because those 3 results were quite different, more different than a random 3% might be. So from this, you can see that once we get to N equals 30, the estimate of CV is close to 5%. So generally we say that 10 is better than 3, you're getting closer. 30 is better than 10. And how many do you need to improve the agreement with 5% over 30? Well, you might need hundreds. So we always say once you get to 30, it's enough. You're going to get an accurate measure of measurement uncertainty. But the variation in uncertainty that you're getting is still much wider. So this is what I'm saying with internal QC. When you run it over 100 or 200 samples, then your confidence in that uncertainty is much tighter. So, so generally with measurement uncertainty, I like to see 30, N equals 30. Now, N equals 30 means N equals 30 measurements, but the other thing is, what about all those other things that vary? Have we measured 30 different scientists? Have we measured 30 different lots of reagent? Have we measured 30 different analyte? I hope I haven't lost you. Can you confirm that you're still there? Somebody?
Yes.
Good. My screen
I'm
changed for some reason. I didn't know why.
Yeah.
Good. Okay, I'll just keep going. So where possible, the guide is you use internal QC material. I'm telling you, I've given you the reasons why internal QC is better than external QA, why internal QC over long periods where N equals far greater than 30 is better than, N equals 10 when you first see a method and so on. One of the issues in measurement uncertainty, which I'm just touching on and I'll lead to a bit later, is that the rounding error. Generally, I don't know whether you realise that with internal QC, we tend to include an extra decimal place in our internal QC compared to what we give to patients as their result. And that's because when we round results, we're introducing a rounding error. So your measurement uncertainty should really include your rounding error. The measurement uncertainty is what the patient sees, ideally, rather than what the laboratory sees. So just consider this issue and read this document if you like, about the importance of rounding errors. I'll come back to that point. This is the point. How do you report measurement uncertainty? Now, ISO 15189 says the MU information must be available to the laboratory user. If one of your doctors rings up and says, what's the measurement uncertainty of albumin? You have to be able to provide it. But how do you provide it? Interestingly, in the uncertainty document, it says it's not routinely with the test result. So it's very rare to see a pathology report that says the albumin is 36 plus or minus 2. That's not how we report uncertainty. Even though that's in principle what we're doing, that we never do it that way. So how do we transmit that concept of uncertainty to the doctor who doesn't ring up and ask for it? Well, if they ring up and ask, if they're stupid enough to ask in our laboratory, we'll give them this spreadsheet and they'll regret ever asking. But in reality, this is the issue. So let's say you've got results from 4 different laboratories for a sodium, and one laboratory reports the sodium as 136.25132, and the other reports it at 135. Which laboratory do you trust? Now, a clinician would probably trust this laboratory because look how precise they are. Well, they're not that precise. They're overstating their precision. So the number that you give to the doctor implies how precisely you can measure it. So the number of significant figures you give to a result is a reflection of your measurement uncertainty. And this was an important issue that was raised by Rob Hawkins, who's in Singapore, across the channel there, when he was working with Roger Johnson in New Zealand. And he's saying that you should be able to use your analytical SD, because this was before the days of uncertainty, to work out what is a significant difference, what's an analytical difference in 2 results, which is 2.77 times the SD. Now, if that 2.77 times SD is less than 1.9, then you can round to the nearest decimal place. But if it's less than 1.9, then you should round to a whole number. If it's less than 19, you should round to the nearest 10. So let's just look into that a bit more. This is typically how we'd report liver function tests over 4 different days. And the doctor might ring up and say, is this patient getting worse or better? Because all the numbers are changing. Now, are we in the laboratory, are we sure that these numbers are changing? Is 29 different to 27 when we're measuring bilirubin? If we repeated an analysis of 29, could it be 27? In which case we can't tell the difference between 29 and 27. So using this measurement uncertainty, we can calculate the 2.77 times measurement uncertainty. And what it tells us is that unless bilirubin changes by 4 micromoles per litre, they're not different. But that's not the message we gave to the doctor. So now if we looked at which ones are different, 29 is different to 38, but 27 isn't different from 29. So ideally, if we use the scheme that Rob Hawkins and Roger Johnson published, and actually Tony Badrick published some more work on this with Rob Hawkins, but he said this is what we should be representing them is this. If we rounded them to the results that our uncertainty represented, the doctor would easily be able to see that, yes, 30 is different to 40 and 30 is not different to 30. Now, even though this is what I'm telling you we should be doing, using our measurement uncertainty to guide how precisely we report results, there'd be fewer than 1% of laboratories in the world that do this. This is something that we haven't really done properly. But this is one way that we transmit the concept of measurement uncertainty. Now, the second question is, we've got measurement uncertainty, and let's say it's 2.7%. Is that good? Is 2.7 good enough for a method? So how do we define what is good enough? The standards say that we must know whether our measurement uncertainty allows medically allowable analytical performance to be created. So that MU tells us whether our assay is good enough. But how? The MU shall be compared against performance specifications. Where are the performance specifications? Now, I'm going to cover this idea, and first I would just want to cover quality. Quality can be fantastic. Quality can be poor, dangerous. Quality can be desirable, like it's acceptable, but close to the optimal standard, or minimal standard, where it's bordering on poor. So quality is not one thing. Quality can be a spectrum of things, and we can aim for optimal quality or minimal quality. So that's a concept I wanted to discuss. Now, many years ago, this question of what is good enough was raised in Stockholm with the IACC. I was fortunate enough to attend this. And what they decided, actually, there was a repeat meeting in 2014, 15 years later, where they revisited, how do we answer this question of how precise a method, or how precise a method needs to be, and accurate. And they came up with a hierarchy, the Milan hierarchy. So clinical outcome, biological variation, and state of the art. Now I'm going to cover that because they're important things, and hopefully some of you have heard of this. So let's say the clinical outcome. How do we decide what precision is required for clinical outcome? Well, here's an example. We know that in diabetes monitoring, a hemoglobin A1C of 7% means patients being well managed. You don't need to do anything. And a hemoglobin A1C of 8% means a patient is in danger of complications and we must do something. So a laboratory must be able to distinguish between 7% and 8%. Well, what precision of assay, A1C assay, is required to be confidently distinguished between 7% and 8%? If your A1C assay has a CV of 2%, the 8% result will vary between about 7.8% and 8.2%. So no matter what happens with a CV of a 2% for an A1C assay, we'll never confuse a patient with 7% with 8%. But what if the CV was 3% for your A1C assay? Now we're at that minimal standard. So, any deterioration in the method, and we won't be able to tell these two patients apart. And if our CV for our method was 5%, which I'm sad to say some point of care methods have a 5% CV for A1C, they cannot distinguish between a patient with a 7% A1C and an 8% CV. So that is below the minimum standard. So using the clinical outcome based on 7% and 8%, we can see that we need an assay with a CV of at least 3% and ideally 2%. That's one approach. Another approach is biological variability. We know that our measurements can vary by CVA, but we also know that a patient from day to day changes according to CVI, the intra-individual variation. And that also leads into another biological variability constant, which is the variation between patients or the reference interval. Anyway, let's say a patient has an analyte which changes with a CVI of 5.6%. It changes with time with this sort of variation, 5.6% variation. You can consider it A1C from summer to winter, or you consider it from cortisol from the morning to the afternoon, or vitamin D, winter, summer. I don't care what it is. You just know the patient is changing and you want your assay to be able to show the patient's changing. Now, if we've got a CV of 0, we know exactly what's happening to this patient. Now, what about if we introduce analytical variation, which is 25% of the day-to-day variation of the patient? So that means the analytical variation is 1.4%, but the biological variation is 5.6%. So here we've got a little bit of noise around what's happening to the patient. Well, we still know what's happening to this patient. It's pretty clear what's happening to this patient. They're higher here than lower here. So this is an optimal standard. We still know, even though there's a little bit of analytical noise, we still know what's happening to the patient. But what about if the analytical noise is 50% of the biological noise? Here, we think we know what's happening. We still think we know. So here, they're probably a bit higher in this period than that period. We don't know exactly what's happening, but we've still got a vague idea of what's happening. Now, once we get to 75% of the variation, so CVA is less than 75% or more of the variation, now we're not quite sure about what's happening to the patient. And if the analytical noise is the same as the biological noise, we don't know what's happening to the patient from day to day. So that is below the minimum standard. So that's how you use biological variation to decide whether your CV is good enough. You just compare it to the CVI. And many of you should have heard of that concept. Now, the last approach is a state-of-the-art approach. We don't know, we haven't got a clinical study, we don't know the CVI. So how do we work out whether our CV is good enough? Well, what about the other labs? What do they do? If I'm as good as the other labs, that's good enough, isn't it? That's the state-of-the-art approach. So, but the problem is, we looked at our EQA program in Australia, and back in 1993, for all of these assays, the CVs were pretty poor. But compared to nowadays, the CVs are a lot better. So if we had have said 1983 was good enough, well, then we wouldn't have changed over the next 20 years. So the problem is that we don't know what's good enough when we just compare themselves to other laboratories. The other interesting thing with this is that really our methods changed a lot, improved a lot in the late 80s and 90s, but they haven't improved much over the last 15 years. Our automated instruments really haven't progressed much in the last 15 years. And that's a pity, because when we compare the state of the art against biological variation, you can see that sodium methods, even though most labs have the same performance of CV, like between 1% and 2% for sodium, virtually none of our methods can monitor a patient from day to day. Whereas in other methods like ALT, patients vary a lot from day to day, and our methods is way better than we'd ever need to monitor a patient from day to day. So anyway, that's one of the problems with state of the art. It doesn't really give you a true reflection. Now, and really when you see, now some people get their what is the state of the art from their EQA program. You better understand how your EQA program set their analytical performance specification. If you're trusting that, it may be state of the art, it may be biological variation. In the EQA program, we do use biological variability. So we describe in the Australian program that ALT is based on optimal imprecision according to biological variation, rather than state of the art. And if you really, I urge everyone to understand biological variation, because it's a key to a lot of things and something. And you don't need that book. You can go to the EFLM website on biological variability and look up any CVI that you need. And there it will calculate your performance specification based on CVI. So here the hemoglobin A1C has a 1.2% CVI. So really the expected minimum performance specification, CVA, is 0.9%. Now, very few hemoglobin A1C assays have a CV of 0.9%. They're starting to approach that, but very few of our assays are actually fit the biological specification for that. Now, we've said that measurement uncertainty is important for interpreting results. Well, let's have a look how that works in practice. How do you use measurement uncertainty to interpret results? Now, this is first of all a result and a cutoff. So here's a cutoff. Let's say this is the cutoff for fasting glucose or cholesterol or ferritin. I don't care which method it is. There's a cutoff and you've got a result which is above the cutoff. But your measurement uncertainty says that that result, it tells you what the spread of that result might be in your laboratory. So when the cutoff is less than 1.65 SDs below the result, it means that when you reassay this patient, there's a chance that their result may be below the cutoff. Measurement uncertainty tells you about how confident you are that this patient is above the cutoff if you measure them over and over again. So it's only when that your result is more than 1.65 times your standard uncertainty above the cutoff that you can say, I'm confident that this result is above the cutoff. Now, I'm going to show you an example of this. Glucose has a CVA of 2.4% in our laboratory. Don't worry about this. I mean, other than to say that 2.5% is less than half of 7%. So we know that our precision is good enough for biological variability, but now we're going to see how it applies for interpretation. So we've got a patient with a CV of A1C of 8.45%. Now, according to our uncertainty, that 8.5 may vary from 8.1 to 8.9. So no matter what, it's always going to be above 7, and we can say this patient's diabetic. The other way we can look at it is if we include the day-to-day variability. If we had to guess tomorrow what this patient would be, including CVI, they would be between 7.3 and 9.7. And that means we're pretty confident that even tomorrow, this patient's fasting glucose, if they'd truly collected it fasting, would be diabetic tomorrow. Often when we recollect a fasting glucose, it's mainly to make sure that the patient fasts properly this time. What about this patient? Fasting glucose 7.5. Now, if we measured 7.5% over and over again in the laboratory with a CVA of 2.4, it would always be above 7.0. So we're confident that this patient's has a fasting glucose above 7, but tomorrow they might not be. And so there it should be. This is a diabetic fasting glucose, but we suggest a repeat. And in this patient here, where the 7.1%, 7.1 millimole per litre, could easily be below 7.1 when we run it again in the same laboratory. So really, I think that this is a borderline fasting glucose. We're saying that we're not sure whether this is above 7 or not. Our measurement uncertainty tells us we're not sure if this is above 7. So it's a borderline fasting glucose, and we suggest a repeat. So measurement uncertainty gives us an idea of how confident we are that a result is above the cutoff. Now, the other thing is, this is just that extension of, well, what about if we measure it twice? If we measure it twice, our measurement uncertainty improves. And so, but in a way, if we measure it twice, we're still pretty sure that 7.5 lies between 6.4 and 8.6. If we measure it in the laboratory twice, it doesn't improve things because most of the variation is due to the day-to-day variation. So really what we want to do with the patients who've got this wide unexpected uncertainty is to repeat it on different days. And when we repeat it on different days, we might get more confidence. But here, in a way, I'm saying with a hemoglobin A1C of 7.5%, even if we measured it on 4 different days, we might not be confident. And really, to cut a long story short, that's why we like A1C as a diagnostic tool. Fasting glucose is not a very good diagnostic tool, even if you measure it on different days. Okay, now remember this problem that we had about a patient who's changing, and we're trying to work out, are they really changing or not? And measurement uncertainty came into that question. But this is a different question to being above the cutoff. When we say, is 29 different to 38, 38 is not the cutoff. 38 is another result with uncertainty. Both the 29 and the 38 have uncertainty. So when we're looking at 2 different results, we need to consider the uncertainty of both results. And in that situation, to cut a long story short, we've got 2 lots of uncertainty and 2 values. So it's a square root of 2 multiplied by the uncertainty. So it's square root of 2 by 1.96, which is a confidence interval, by CVA. So it's 2.77 times CVA. So what we're saying is those 2 results need to be 2.77 measurement uncertainties, standard uncertainties apart, for us to be confident that they're analytically different. Remember the difference from a cutoff was 1.65. The difference between 2 results is 2.77, but they both use measurement uncertainty. And this is what's usually called the reference change value, a delta check. So are any of these results different? We said, yes, some of them are analytically different, but when we include the biological variability between the 2 results, and we can calculate that out, here's the analytical uncertainty, here's the biological uncertainty. So albumin needs to change by 8.6%, but before we're sure that this patient has changed from one day. Changes by 3.1%, it's 2.77 times 3.1. We're sure that the analysis is different, but 2.77 times 8.6 means the patient has changed. So yes, some of those results are analytically different, But when we calculate the critical difference of total uncertainty, none of these results are different from a day-to-day basis. So we could use measurement uncertainty and biological variability to actually statistically say, this patient's not changed. This patient hasn't changed. Some of the analyses may have changed, but the patient hasn't changed. So it shows you how important CVA and CVI are to the interpretation of results. And Callum Fraser, actually, even 20 years ago, this is a report, I don't know, 2001 from his laboratory in Scotland, he used to put flags on his report to say, this result is significantly different and this result is rising. So, for example, this this ALT may, which result we will look at? This magnesium may be normal, but it's rising. So there's a lot of information we could transmit. And this is briefly just some stuff that we've been doing in our laboratory. You can use these calculations, measurement uncertainty and CVI, to flag episodes that have changed by looking at the total changes. And we've done that in our laboratory. So here's an example. A gamma GT that's changed from 86 to 133. We're more than 95% sure that's a change. It's a Z score of 3. An AST that's changed from 11 to 24. Both of them are in the normal range, but that's a major change in ALT. Why do we have to wait till that ALT is abnormal before we let the doctor know the patient might be getting sick? So these are really important things for the systems of the future. Now, not many laboratories can do that, and even my laboratory in Melbourne is only beginning to be able to have that capability. But CVA, understanding your measurement uncertainty, and CVI gives you this capability to provide much more clinical information than we're currently providing. Now, how often do we need to review measurement uncertainty? And I think there was a question on the chat recently about how often do you need to do patient comparisons or something. In the ISO 15189, it says MU evaluation should be regularly reviewed. Well, it doesn't really answer the question. It's like, how often do we need to review them? Updating interim. If there has been a significant change in a measurement system or a new measurement procedure has been introduced, you must do it. Now, what about if there's a significant change in the measurement system? How do we know that? Well, if your QC or if your EQA has got a problem, you might need to re-estimate your measurement uncertainty because it could be that the method has now changed. The analyzer's getting old, the reagents have changed, your water supply has changed, whatever. But whenever there's a QC failure that you haven't explained or an EQA failure, you might need to repeat that to be sure that your measurement uncertainty haven't changed. And that's about all I can say about that at this stage. So MU, it's an ISO accreditation requirement. It's clinically necessary to make sure that our reporting is appropriate. It's necessary to make sure that our assays are doing what they're expected to do. And it's also necessary if you want to properly interpret results. So thank you. That's the end of my talk.
Thank you very much, Prof. Kansikaris. Very interesting presentation. We all the participants learn about what is the uncertainty, how to calculate, how to report, the interpretation and the implementation, and how often we need to renew and review. And today all are very interesting topic and presentation. Now let's move to the Q&A session. I hope all the three speakers can join us. Okay, there are many questions that already in the Q&A. First, the question is from Muhammad Joka Yahya. Based on the, I think this question is for Dr. Xian. Based on the presentation, it appears that the focus of risk management is primarily on the risk to patient in terms of quality outcomes. However, Does the requirement for risk management also extend to laboratory personnel in terms of safety? What is your experience in Indonesia? Please, Dr. Xiang.
Thank you for the question. I think there is a requirement for the safety of the personnel itself, because in the requirement is that the laboratory should provide the facility and environment condition to ensure the safety of the patient and also the personnel. And also in some other requirement, indirectly it mentioned that it should also be, provide the facility or the equipment that is intended for use. Intended for use is also, I think, we can also regard it as also safe for the one who use it. And in our experience in Indonesia, usually it is the safety of the personnel is also audited during our ISO assessment.
Okay, thank you very much, Dr. Xian. Is there, you want to add something maybe from Prof. Ken Sikaris or Prof. Tony Bedrick regarding to this question? No?
I mean, certainly I agree that the ISO 15189 does mention safety of patients and safety of staff and everything. But in our country, we also have some national requirements for, employee safety, which in a way are even more important than the ISO 15189, because they're the laws that the courts would use to put you in prison.
Okay.
In our country also.
There's another question that's anonymous. Does ISO 15189-2022 apply to the phlebotomy service, including staff phlebotomy competency and hand hygiene provided by the lab to clinic patients who visit the lab for phlebotomy?
Yes, of course, since all the personnel that have impact on the patient care, have impact on the validity of the result, will has to follow the requirement of the ISO 15189. So they will also have to apply all the requirement. We also do the assessment in the phlebotomy site for the requirement of the 15189. And also actually, like the first question is, for the implementation of the ISO 15189, there is also the national guideline, the laboratory practice, and other standards also apply. So we have to combine all and see which one is higher than the others.
Okay, thank you, Dr. Xian. And we move to the third questions. I think this is interesting for all the lab staff. Or how frequent, this is the question from Lo Yokli. How frequent do you think the lab should conduct comparison studies? Do you think we can use risk management approach in managing how frequent we need to conduct comparison study? For example, if the test was statistically equivalent to another similar instrument in the lab, can we do it less frequently? I think I would like to invite all the speakers to answer these questions. First, maybe from Prof. Ken Sikaris first.
Yes. Yeah, you don't. I mean, some labs do it regularly. They'll just send patient samples around between instruments regularly. They call that internal EQA or something like that. But really, as a minimum standard, whenever you suspect that the two analyzers, which you're monitoring with your internal QC, when you suspect those two analyzers are now different, the question is, have you affected patients? And it's the same applies to EQA. When your EQA shifts, you need to confirm with patient results, is this affecting your patient results? So we generally use, IQC warnings or EQA warnings as risk incidents for patients when we think we need to be sure about whether patients are affected, therefore we need to repeat some patients. So I think that's the minimum. Ideally, it's handy to run them every now and then, but just so that it's an extra quality assurance tool. But as a minimum, whenever you think the thought enters your mind that patients may be affected, I'm not sure, you better check some patient samples.
Okay, thank you. Maybe any comment from Prof. Tony Bedrick about this question?
I agree with Ken. It's really, this should be part of your EQA process. That's why we have EQA, and hopefully the right sort of EQA. And then if we identify a problem, then it may be that we need to use a range of patient samples.
Dr. Shan?
Yes, thank you. Actually, when we first introduced an equipment and we use the different equipment or different site for that equipment for one test, for the same test, then at first we have to compare it first. And then when there is, as the Dr. Ken Sikari said, we have to monitor that using the IQC, using the AQA. So we know if there is any change, then we have to do perform again the comparison. Or when we change the method or we change the sample preparation, then maybe it will affect the comparison. So we have to re-perform the method comparison.
Okay.
I will add one other thing. Often the EQA results you won't get for 2 weeks after you've submitted the results. And so, your question is, was my assay shifted back then 2 weeks ago? Now, the method may have resolved now, but and this raises the issue about using patient results, your existing patient results, like patient-based QC. Because we can look, you can extract out of if you've stored them in the computer, you can extract your patient results and look to whether your patient means have shifted. That's an easy way of doing an immediate patient comparison. Your method has shifted, your QC has shifted. Well, look at all the results that you've reported. Have they shifted as well? Has your patient median shifted? And that's something that is a really valuable tool, and it saves you a lot of effort if it can show that there's not a problem.
Yes, I think one thing that we can add also in monitoring the QC, we can see from our IQC peer group, because it is some of the instrument give us real-time result that we can compare day by day, whether we have shifted from our the result that we should obtain. And the other one is maybe as the ISO 15189 has already stated, that maybe we have to perform the IQC in a way that can detect the lot-to-lot variation, so that more information can be given from the IQC to see whether there is a shift or there is a trend in the IQC result.
Okay, I would like to continue to another questions. How about if that you said it from the peer group, the result is like a shifted in the IQC in the peer group, but the result from this IQC in the peer group is already like out of range from the manufacturer range QC. Is it still allowable?
Pardon? The shift is more than?
I mean, in the peer group, the IQC is shifted all of the result in the peer group, and if we compare the result is shifting in the peer group to if we compare it to the range in the manufacturer, actually it's already out of range in the manufacturer QC range. So is it still allowable or?
No, I think we have to have guideline for our IQC procedure. using it's best to have the lab-based quality control rates to detect more earlier of the shifting or of the imprecision, because usually the lab quality control material have higher range interval. And also, if we have something happening, according to me, we have to see what is actually happening, whether there is a change of the accused material, calibration or control, or there is a change on the procedure or something happening with the instrument itself. Because we have to be cautious. It's easier to correct it at once than have to check all the specimen before that something happened.
I think it sounded to me like that was possibly due to a lot-to-lot variation. And I think if you rely on QC to detect lot-to-lot variation, you will wait a long time. I don't know, it depends on the assay, but often people will run a QC sample at the end of every shift, or once a shift or once a day. When you take into account how long it will take conventional QC if you run that against 2SD, how long it will take you to pick up that there's been a significant change, it could well be days. So if you suspect that you've got or you detect that you've got a lot-to-lot variation between reagents, you need to test before you put the new lot of reagent in. If you know that it's highly likely that there is a chance of lot-to-lot variation, you need to test each new lot using patient samples, stored patient samples, and not rely on a QC sample to pick up lot-to-lot variation. And I think what Ken said is also very true. That's one of the advantages of using patient-based QC, that the patient means or medians that you're using, you're tracking them all the time. And even if you have to use 60 samples to give you a good mean, that will be, I suspect, you will detect a shift long before conventional QC will detect that shift.
Okay, thank you. Thank you very
I'll
much.
tell you, I will tell you what we do in our laboratory, because it agrees with what's been said before. Whenever we get a new reagent, we run it in for a week. We run QC on that reagent for 1 week before we report any patients. Because as Tony says, it takes a while to realize whether that QC is truly in, like your 10x score or 41SD scores. It takes a while for you to be confident that the new lot is okay. Now, it does mean you've used up, well, it's not that much. If you run the high and low QC twice a day for a week, you've done 20 assays, and out of a 500 test kit, that's not a lot of not to use up once when you've started up this new reagent. So I would, if you can manage it, run that reagent for a while before you use it. Otherwise, you'll get a surprise.
Okay, thank you very much. There are so many questions coming. I will choose some interesting and the same related questions. How would you adopt? This is from Rukman Awang Hamad. How would you adopt ISO for labs in low middle income countries? Would it be possible for them to achieve acceptable requirements? Maybe Prof. Tony Bedrick or want to answer first?
And that's a tricky question, because it depends on what resources the laboratory has in place. That's, you're talking about a wide range of capability, and in terms of there could be issues with getting reliable reagents, being able to pay for sufficient QC and EQA. But really, the 15189 represents a sort of the base level of quality that we demand in laboratories. And there's a lot of aspects of 15189 that are not just about assays; they're about training and all other sorts of procedures that need to be in laboratories in terms of ethics and maintaining equipment, etc. So all of those things should be applicable in even in those resource poor countries, I would have thought. It may be that some aspects can't be controlled as well as others because you can't afford sufficient controls, but certainly I would think that laboratories everywhere should aim to get as many of the clauses of 15.189 in place as possible. It really does represent the base level of the expected quality to reduce patient risk.
Dr. Xian, any experience maybe from Indonesia about adopt this ISO for labs in low and middle income countries?
I think in Indonesia, we follow the ISO 151 because the ISO 15189 requirement are the requirement that how to provide qualities like Tony said. So it should, even though there is limited resources, but the standard should, the procedure should follow in such way that the person can show that it is still well managed and can still prove that the validity of the result is obtained, such like quality control. Usually in the big lab, they do it every day. But in the small lab, they do it only once a week. They don't have to do it every day. They can do it every time they have specimen. And for the POCT, it's according to how stable is the test itself. You don't have to do it every day. Maybe if it's stable and if the equipment itself have like the internal control or something, you don't have to have the laboratory information system to have the proper to have fulfill the management requirement. Even with the manual one, you can fulfill that. It's according to me, but because we also assess the small laboratory, just how they can manage their tests according the use for the patient. Usually they use POCT. Most of the lab use POCT.
Okay, thank you. There's a question for Prof. Kensi Karis. How do we calculate? This is from Anonymous. How do we calculate measurement uncertainty for a single assay on multiple instruments? Do we calculate individually or do we combine into a single uncertainty? And second question is, should bias be included into measurement in uncertainty calculation?
It's a very good question. And it's, in a way, when you've got your SD on an instrument, you want to work out whether that instrument is changing. Now, so there you do need an SD which monitors the instrument, because you don't want the instrument. And instruments are different to each other. In our laboratory, we have many. You'd be shocked at how many instruments we have. We might have 10 instruments measuring sodium. And there is a bias between one instrument and the other, permanently different by 0.1 or 0.2 of a millimole of sodium. So we don't want to wait until one instrument, which usually has a low bias, becomes like the instrument with a high bias, because that instrument's deteriorated. So measurement uncertainty can be used to monitor instruments, but the ultimate purpose of the uncertainty, which I described in my talk, is to interpret patient results. And if a patient can go from instrument A to instrument F, it means that uncertainty the patient sample's using is the total uncertainty of all analyzers. So we do have an uncertainty across analyzers, and that's what we give to the clinician, because we're not sure which analyzer the patient will go on. And so even if there's a bias between one analyzer and another that we're not choosing to correct, we'll include that bias in our overall uncertainty. So as long as that overall uncertainty is fit for purpose, it doesn't matter. But the overall uncertainty is what's so the short answer is the important uncertainty is the across analyzer uncertainty as far as patients are concerned. But for your quality control system, you might want to know the uncertainty of each different analyzer so that you can work out whether an analyzer is starting to deteriorate.
And in fact, I was just going to add, a broader question. I mentioned that the different EQA audiences. You know, there's the lab and there's the assessors, but there's also really, you know, the people who write guidelines, or even the people who interpret our results. They really need to know what's the uncertainty generally across, you know, all laboratories. Now, it's good to know that the uncertainty from laboratory A is, you know, 2%, and maybe that the uncertainty from laboratory B is 3%. But honestly, when they interpret results, they need to know what would be the general uncertainty across any laboratory, so I can factor that into my clinical experience when I try and interpret results. And particularly, you know, I mentioned the issue with ferritin and some other tests where there's a really tight cutoff. You know, one question is what method was used to determine that cutoff, but also what's the general uncertainty about that cutoff, you know, in all laboratories around your country. You know, that's critical with the interpretation of results, both those results and also the results where you're monitoring a patient, and what's the sort of change that we can expect purely due to laboratory, you know, uncertainty as compared with pathological, you know, changes. So we shouldn't just be interested in what goes on in our laboratory. You know, we need to be interested in what happens with the results and how they're interpreted. You know, we always need to sort of look outside our little silos and say, well, you know, we've got a great result, but how does that compare with the result from another laboratory? We've got a really tight uncertainty, but how does that compare perhaps with another laboratory's uncertainty? Because somebody else out there doesn't really care about those things. They just want to know, how can I interpret this result? What does it mean to my patient? I think we should never lose sight of that.
Okay, thank you. Because you already mentioned about the EQA, there's a question. Can we use EQA performance to replace UCAL, uncertainty calibrator, for MU calculation? Prof. Tony, maybe you would like to answer this question?
I think if you use the right material, I think you can certainly get from EQA if you have enough samples and it's material that truly reflects what's going on with your patients. I think you can use EQA to calculate MU, and in fact it's probably even safer if the EQA provider that calculates that MU for you or for your instrument group. Really, what in terms of the bigger picture, how do people interpret results? You know, they need to have an idea of what the MU is about that result, and it's probably better because, you know, as well as the issues about what data do I use for MU, people often don't seem to calculate it very well either. They have their own formula for calculating MU when you go around from one lab to another. So it would be good to have independent assessment of MU, and perhaps that could be given as part of the service by an EQA provider if you do enough samples and the material really is appropriate to do that calculation.
Can I ask a question of Tony, because he's a world expert on EQA?
Yeah.
The BIRAD Unity program does collect the information on the lot of reagent. So there is some information in that program, the internal QC sort of program, to be able to differentiate lots. How useful do you think it would be for EQA programs to collect the lot information on reagents rather than just the manufacturer?
I think it's critical. I never used to think it was important once because I'd been brought up as a chemist, but then I got exposed to serology and I realized, you know, how critical lot-to-lot variation is. And now I think we're discovering in chemistry as well that in fact there's significant lot-to-lot variation as well, not just in you know, immunoassays, but also even in some of our other assays. So I think it's important. It's very difficult for laboratories to do it because, you know, we change reagents and we forget that the lots change. It has to be automated in some way. But I think the more information we can gather about our assay, you know, with lot-to-lot, with the lot number as well as the calibration number, I think that all will add to the information that we've got about what's going on with our analyzers. And more importantly, if we can compare how our performance against somebody else, not just using the same analyzer and you know, the same reagents, but the same reagent lot number, that's when we'll really start to learn more about what's going on and potential sources of error. because manufacturers make mistakes. Their processes aren't not completely without error.
Thanks.
Okay, thank you. Very interesting discussion. And I think there's another question related to this also. How about for the immunoassay parameters, such as hepatitis B, HBe's AG, and anti-HIV? If our lab result shows borderline for the uncertainty, should we just refer it to the other lab that has different method? As we know that for the immunoassay parameter, especially for the infectious disease, is there any like the traceability or what? Because we know that the immunoassay parameter that have like a cutoff with the numbers of index or as per CO. Maybe Prof. Ken Sikaris would like to answer these questions.
Tony mentioned the problem of serology assays, and
Yes.
often they're the positive, negative, or borderline assays. Now, it is possible to deal with them quantitatively, but it's sort of almost artificial because what the clinician sees is the qualitative result, positive, negative, or equivocal. And so now you could repeat an equivocal result, and if you repeat it often enough, it might become negative or positive just because of the measurement uncertainty in the process. And so that's just generally considered to be an inadequate approach. The best way to, the standard approach for serology, and I'm not a microbiologist or serologist, but is usually to go to an independent assay to see whether it also gets a negative or positive result, rather than to play with this grey zone of uncertainty of borderline and try to, because generally serology assays aren't monitored truly quantitatively like a lot of our chemistry assays are. They're monitored qualitatively. So I generally, that's what we do in our laboratory. If we've got an equivocal result, we usually go to another platform to confirm whether it's likely to be positive and negative, rather than to repeat the analysis on the same platform.
How about you, Dr.
I think that's key. Sorry to interrupt. I think the other thing that's key with serology results, as with a lot of other results that are qualitative, is that there needs to be really good information given back to the clinician in terms of how to interpret this result, particularly if they're on the borderline. There could be borderline for all sorts of reasons. It could be the patient's getting better or worse, or it's too early. So I think it's really important that lots of clinical information is given to allow the clinician to interpret the result with assays such as that.
Okay, so just repeat with another method or another brand analyzer. It's not a solution to this, right?
If you've got that ability, that's the solution. But if you don't have that ability, I'm not really sure how many repeats are going to give you more confidence in a borderline result. It's borderline by definition.
Okay. Dr. Shah,
Maybe
please.
I can ask to Dr. Sikaris. Is it possible to run by two other different methods that are more sensitive or have the more precise? And
yeah, ideally the second method is better in some way. Like it's a better antibody, a better. I mean, often we're doing serology and confirming by PCR, like that's ideally the second method is a better method. And even in drug toxicology, which is another example, our screening method is qualitative and our confirmatory method is a better method, like chromatography. So ideally the confirmatory method should be a better method. It doesn't really make sense to say, I'm going to repeat it by a method that's worse. So it's much more logical to repeat it. If you repeat it with an equivalent method, I agree with what you're implying, was that so this method says it's borderline, this method says it's positive. Well, which one will I believe? Do I have to do another one as a tiebreaker? So it's awkward when you're repeating with equivalent methods. Ideally, you're repeating with a better method so you can have confidence in the second method.
Okay, thank you very much. And there's also another interesting questions. The result of D-dimer. I think that's also a problem for us too. I experienced a variety results for D-dimer sample performed using different analyzer or systems. The difference among systems were so great. So how is the development about D-dimer traceability? Maybe about traceability, Prof. Tony Patrick, I think.
I honestly can't answer that question. I just don't know. I don't know anything about D-dimer traceability, unfortunately.
Okay. Any speakers want to answer these questions? But
No, I don't.
D-dimer traceability.
One thing there is reference material for D-dimer at present. And D-dimer consists of different particle, the long one, the short one. So it depends on which epitope they will target. So that's we found many difference when doing D-dimer with different platform.
Oh,
At present, so as far as I know, there is no reference material for the D-dimer.
okay. Thank you. Maybe let's jump into the POCT. As we know that in ISO 15189/2022, there's like another rules for POCT. So there's a question from Lucia Sinchugunawan. How do I select the best POCT equipment? Should I make study comparative with the gold standard technique? Maybe this means to the analyzer. Is there any calibrator for all POCT equipment? How to calibrate POCT example for the lipid profile? For the first question, the study comparative with the gold standard technique, maybe I will ask Dr. Xian, and the calibrator of the POCT, maybe I would like to ask to the Prof. Tony Patrick. Dr. Xian first.
I
Okay.
think it depends on what is the intended use of the POCT test. Because for screening, for diagnosis, or for monitoring, the intended use will be different. And for the POCT, if it's used by the different operator than the laboratory technician, then maybe we should consider also the easiness of use and also the maintenance and also the stability of the reagent itself. So not just the specification of quality, but also how to use it, because it is difficult to keep the competency of the person outside the laboratory, because they just do it once in a while, not every day, something like that for the POCT. And I think what's the other question, Dr. Tirsa, is
About the calibrator,
standard?
for the POCT equipment and how to calibrate for the lipid profile of the POCT.
If the POCT is in an institution like a hospital, then maybe it should be compared to the method in the central lab. But some of the laboratory have it POCT, just POCT and do it in the clinic, something like that, but not doing it in the laboratory. Then still they have to have the EQA for comparability and the internal quality control to ensure the monitoring of the quality.
Prof. Tony, you would like to add about the calibrator, maybe?
Yeah, I think that's fair enough. I always think that QC and what Dr. Shan said about fit for purpose. That's the whole crux of the matter with point of care. It's often used for a different purpose, but still you still want to maintain comparable results with other systems. But remember, with point of care, usually point of care you're using a finger prick, so it's a different matrix. It's whole blood. There's going to be different values, I always think that there are two aspects to point of care. There's the instrument itself, so that's there's usually a cartridge or some device like that that's used, and they're really mass produced in a factory, and they've got really very high tolerance, so there's very little that can go wrong. But QC of batches is important, just to make sure when a new batch of cartridges or whatever comes in, that you do some sort of QC to ensure that you're controlling that the cartridges are giving the same result as they should. But more importantly, with point of care devices, I think is the operator. Most errors are related to operator error, not just in the process of putting the sample in, but also using expired cartridges, recording the result, ensuring that the result goes somewhere, goes into the patient record, maintains the equipment, maintains their own training. I think that operator competence is the key to the issues with point of care devices. To be honest, that's where the focus should be.
Okay, thank you. There's another question about POCT also from Dr. Rosinta Cristina Solin. The new standard requires that the frequency of POCT QC be based on stability and risk. Does this have guidance from ISO? How should we evaluate this stability? Thank you. Maybe this is for Dr. Xian first.
Okay, and I think there is some journal that explaining how to do the IQC in primary healthcare that consider the risk of the test itself, and also the easy and the user friendly of the method itself, and what kind of instrument is it itself, whether it's a cartridge based, manual based, or liquid based, something like that. And also with align and also they consider also the frequency of how many tests is done by the operator, and then they decide how many times should the IQC be done. I think the stability can be seen from when they are doing the IQC day by day. They can see whether the tests are stable or not. And also they can see when they watch the patient result, whether the result from the tests are stable or not. That's one of the things they can study to see the stability of the POCT test.
Okay, thank you. There's a question from Julie Sharfan to Prof. Badrick. If the lab has demonstrated that a method is not traceable back to the reference standard material, it means by running patient sample against the manufacturer's calibrated versus the SRM, rather than applying a post-analytical correction factor, would advise that the lab use the SRM value to recalibrate the method in addition to informing the manufacturer?
Labs don't usually have those materials. Those standard reference materials are usually expensive, and so it's not that easy to get that material. I guess if you've got that material and you want to recalibrate your assay so that you're sure that it's traceable, that would be one option. But I think laboratories always have to be careful about doing things like that. As I said earlier, the problems we have is related to traceability are that different assays get different results on the same sample, and the issue with interpretation comes about how are these results interpreted? Are they interpreted against a reference interval, or are they interpreted against a decision point, or are they interpreted in terms of looking at changes in a patient? If a lab has a reference material and they calibrate their assay and therefore change, relatively speaking, their results compared with what they were getting before. They need to be aware that they haven't changed any of those other factors. Is it still valid to use the decision points that were being used before, the reference intervals? What about patients that have already been, results have gone out and they're being monitored? I think that there are lots of issues that you need to be aware of. And if the whole assay has changed, a factor would be, I think, important to bring the results back into line with what you were getting before. But I think to bring in an external standard, if you've got it, I think that you'd have to think about that very carefully.
Okay, thank you. There's a question to Prof. Ken Sikaris. Should the uncertainty value be evaluated at the clinical decision limit rather than the reference value? What do you think?
Very good question. Because the measurement, that ultimate purpose of measurement uncertainty is to fulfill its clinical purpose. The clinical purpose is most important at those clinical decision points. So now sometimes we don't have clinical decision points, like for sodium, there's 135 for the lower limit and the upper limit. So it's important to know the uncertainty at the lower and upper reference limit. But for other things like glucose, which I showed, or A1C, it's more important to know the uncertainty at that clinical decision point so we can decide whether the patient is clearly above or clearly below the decision point. There are some other decision points that we use for all assays, like the critical limit. So we'll phone through a potassium when it's over 6.5, let's say. Are we confident that it's above 6.5? Does our uncertainty estimated at 5.5 apply to 6.5? So it is handy to know that. And usually the manufacturer or laboratory has an idea of the functional performance of their assay. What is the range of reportable results, the analytical range? So I think that the answer is yes. The best place to do measurement uncertainty is at the clinical decision points, and the fallback is to understand how your assay varies in its precision across the analytical range.
Okay, thank you. There's another question for Prof. Tony Bedrick from Julie Shervan. For a measurement with two reporting units, such as percent in A1C and also SI units in A1C, is it possible for one unit to be traceable and not for other?
I think that's an interesting question, but really the units are transformable. You can transform one into the other. So I think therefore. And they are traceable, so I think they're both traceable, but you just transform one into the other.
Okay, thank you. Question for Dr. Xian from Chong Chan Eng. For CE-IVD diagnostic products that have been not approved by local regulatory authority to use in diagnosis, but imported as RUO, research use only, should the lab performs a full validation or verification only?
Okay. First is you can ask from the manufacturer whether they have already done the validation study. If you are not sure whether the validation study has been performed, but I think the local regulation should be followed first, because the regulation is in each country will be different. Either this is an RUO or not. But if the manufacturer say that this is already validated, maybe you have to ensure and make them give the validation study and see whether the validation study is already appropriate or not. Because usually it will be the IVD will be regulated as IVD also, but maybe something else that make it imported as RUO, maybe because different intended use or something. This must be clear first. Maybe Dr. Tony or Dr. Ken have any experience regarding this?
I think with limited experience in assays like immunohistochemistry, with these sort of research reagents, I think you need to do local validation.
Okay, with the local validation. How about you, Dr. Sikaris?
I mean, we have regulations in Australia, and generally when you've developed an in-house assay, you're allowed to use it, but you should warn the clinicians that this assay is unvalidated. So, and do whatever validation you can. Ideally, send that validation to the national authority so that they can improve the validation of your assay. But if you don't, and you still want to use it for research or for clinical purpose, you have to be very clear to the users of that, the lack of external validation of your assay and the uncertainty, that any uncertainties you have in your results, because I know that, you know, I mean, we do want medicine to progress. We want new assays to be developed, and they have to start somewhere. But the important thing is to be transmitting, you know, the confidence you have in that result honestly to the clinician who might be using it for the care of the patient.
Okay, thank you. There's a question from Zulhainan Hamza. The alignment of ISO 15189-2022 with other ISO standards such as 17043, 17025, and others will strengthen the implementation of the ISO 15189. But how far that we can apply those other ISOs as only a guidance for the laboratory or as part of a needed document during the assessment? Thank you. Maybe this is for Dr. Xian.
Okay. As we can see when we read the ISO requirement, it's something like general, not step by step how to implement that requirement. So the guidance give the step by step or more details process on how to implement the requirement. And this is one of the things that should be followed by the lab when they implement ISO 15189. But other standards like the national standard, national regulation also apply in the implementation of ISO 15189. So it's not only just for presenting it as having it as a guideline and not implementing it, because they said that they or we just have it as documents, if I'm not mistaken, the question.
Okay.
So we have to implement the standard.
Thank you very much, Dr. Xian. And there's a question to Prof. Tony Bedrick, anonymous. How to set a reference interval for each parameter and each age classification? Is it okay to use reference that is given from the manufacturer or maybe from the studies, the journal?
I think reference intervals are key to interpretation of results. I think you can use the manufacturers initially their guidelines, but really the best option is to adopt a reference interval based on a lot more patients than you've got no idea when a manufacturer gives you the reference interval, how much data they used, how many patients, etc. What was the range of patients that they used? You know, I think that laboratories, or better still, national organisations, where possible, should develop reference intervals for general use across laboratories using really patient samples. I think the indirect method is the more effective way of developing reference intervals, and labs should not just adopt, unless it's a very unusual assay, very rare assay, they shouldn't adopt reference intervals from manufacturers. But I might ask Ken, who's the expert on reference intervals, to give some more input into this question.
Please do.
Now, the only thing I'd add, I'm on a committee called the IACC Task Force on Global Reference Interval Database. So they're aiming to provide two things: to provide a database so that you can go and hopefully, let's say you don't trust the manufacturer's reference intervals for, well, has anyone ever published for Malaysia or for Singapore or in Indonesia? Has it been published? We don't have a way of easily finding that information. So one of the things we're hoping to do is provide a website where you can find that information, like the biological variability database that EFLM have had. And the other thing which Tony said was that I think laboratories underestimate how useful the data that they have is in determining their own reference interval by this indirect. When you pull out all of the data for your albumins in Indonesia, it'll follow a Gaussian distribution, and it'll reflect what the true reference interval is. You just need the statistical tools to be able to understand your laboratory data. And it doesn't even have to be an individual laboratory. You can pool, if you've got the same method in different laboratories, pool the data from different laboratories, because you do need a fair bit of data to do this. So I do agree with Tony. This is the way of the future, that we don't rely on manufacturers testing 40 German people 40 years ago to tell us what normal is. We really need modern methods of determining reference intervals. I will say that I wouldn't ignore the manufacturer's kit insert. Some people use a textbook which is 40 years old rather than a manufacturer's kit insert which is 10 years old. Well, that's a mistake too. So really it's to use the most up-to-date information that applies to your method and your patients. And if that's in the kit insert, well, then that might be the best interval you can get at this stage.
Dr. Ken, usually in our country we have to comply to the regulation of the ISO that we verify the manufacturer reference by testing 20 healthy individual. But the difficulty is it cannot cover all the age
partitions. Exactly. No, it's very hard.
Look,
in the standard, it actually says that you don't have to do everything, unless you think they might be different. If you think that thyroid behavior, the TSH molecule is different in pregnancy than in others, you might have to validate pregnancy separately. But if you can assume that the analyte is the same, or the matrix is the same in all partitions, then you only have to validate one of the partitions. It says that in the ISO standard. So you don't, I agree with you, ideally you should be, but it's very hard. I mean, when you consider all of childhood, neonates, infants, puberty, young adults, postmenopause, premenopause, pregnancy, first trimester, second trimester, it's impossible for any laboratory to validate reference intervals. But you should at least validate one, and ideally the one which applies to the most common partition in your testing population.
And I think it's also a little bit difficult for the pediatric reference interval.
Yes.
It's quite challenging.
Yeah, well, the pediatric thing is, the problem is that pediatrics don't, even when I said neonate and infant, it's not as if when they're 1 month old, they suddenly change overnight to be a different type of child. It's a continuous change. And so the way forward on that, and Jacob Zierk, who's a young German pediatrician who's on a IACC committee, he's really trying to promote the use of continuous reference intervals. Now, continuous reference intervals are very difficult for laboratories to adopt because our LASs, our reporting systems, don't allow usually for continuous reference intervals. But we can still provide resources like a growth chart, a piece of paper that says this is how the reference interval changes in a child, or in pregnancy or anything else. So you don't have to provide the information on a report. You can just say to the clinician, we've got that information available if you want it.
Okay, thank you very much. There's a question from Busadi Pratumfinit. Sorry if I mispronounce. The question is to Prof. Sikaris. From the graph compared between CV of EQA and CV of IQC, CV of EQA means the CV from the participant lab or CV from repeated EQA samples.
Well, yeah, it's sort of touched on what Tony was saying. So the CV in that graph was the CV for that laboratory. So for the samples that that laboratory submitted to the EQA project. Now, it doesn't mean that was the CV for the EQA sample, which we repeated 30 times in the laboratory. That's not what it meant, that graph. But that would be, I don't see what the point of that is, because you may as well repeat a patient or your internal QC sample if you want to get that sort of estimate. But I agree with Tony that the overall CV contains some new information. Like if you compared your internal QC with the CV of all laboratories, that's a different question altogether. But anyway, that graph was just the results that individual laboratory submitted to the EQA program and how that QC compared with their internal QC.
Okay, thank you. Let me see, let me check first if there's another. Oh, this is about the POCT. Are there any recommended proficiency testing for POCT tests? Can split samples be used for POCT tests? Maybe Dr. Xian would like to answer these questions.
Actually, what means by POCT is not only manual tests or rapid tests or the very simple tests. So it can be also the big equipment, but put outside the lab. So there are many proficiency provider that can handle. There are many proficiency provider for the POCTs. You can have the blood and gas analyzer in the ICU or hematology analyzer in the ICU, something like that. There are proficiency test provider for that. But how to choose it is better to have a proficiency provider that is already accredited with ISO 17034, if I'm not mistaken. Then it means you don't have to obtain data from the provider for the appropriateness as proficiency provider. So choose the one that already accredited, but 170 or 0.43 ISO. And can be we can do the proficiency testing for VOCT by doing one sample and comparing it to other labs, but not to the same lab, in the same lab. So we know compared to it was compared to different labs.
Okay. Okay. Thank you very much, because we are running out of time. I'm very sorry if there are questions that I cannot read or ask to the presenter. If you still have questions, maybe you can email us and we will ask your question to the presenter. And I would like to remind to all the participants, for the attendee link absent, it will be given directly to the email. So if you need, please allow me to speak in Bahasa, because many Indonesian participants will take the CME credits. Jadi untuk para peserta yang untuk pengumpulan SKP di Pelataran Sehat akan dibuka hari ini pukul 5 sore untuk mengikuti pelajaran. Dan untuk link absen itu tidak akan diberikan melalui Zoom ini, tetapi secara otomatis untuk seluruh peserta yang mengikuti Zoom ini itu sudah terdata oleh panitia dan akan diberikan email untuk kuesionernya. Jadi harap tolong diisi tentang kuesioner dari acara ini untuk bisa mendapatkan sertifikat dan diverifikasi di LMS Camcast. Jika tidak mengembalikan kuesioner, maka tidak akan diberikan untuk akses pembelajaran di LMS Camcast. Seperti itu. But for the international participant,